fraction of second. So one cycle is 20 millisecond. Here it is 60 hertz, so it is 16.67 millisecond. So it means any changes either side will be changing frequency, and that changes will happen in a fraction of second, in a millisecond or microsecond. That's the one big reasons or problems. And second problem is it cannot handle large deviation. Means if changes are very high, then it is not acceptable. Means always it should be very closely equal, balancing. So this is a trickiest point of the electricity markets or electricity industry, and which create a lot of trouble, or you can say issues, on the operators and of course sources and all. So these are the some of the serious issues of electricity industry over the other industry. Like if you talk about the other industry, for example, airline industry or oil and gas industry or any other industry, if demand and supply changes, so they may not reflect immediately, okay, not in a fraction of seconds. So they have a time like couple of days or weeks or month to reflect. And also there is a warehouse where they can store if surplus demand, surplus supply or so. So they have a time to think and plan. But here there is no time to think and plan unless you shut down and then think and plan, which is not acceptable. Sashi, is it okay? My voice and
yes, sir. It is very clear. It is very clear, sir.
Okay, and speed. I'm going
comfortable.
fast.
Comfortable. Okay. It's smooth only.
Okay, thank you. So these are the some inherent issues of the current, or you can say electricity industry, which create a lot of other requirements. So not going much details about electric industry. What is a smart grid? So you keep in mind it is not a grid. It means grid was not smart earlier. It is not truly or fully. It is not. You can say full truth. It is partial. Already there was a smartness. And smartness means fast communication. What are the smartness? What is the smartness? In a person, just talk about persons. What need to be a smart person? So to be a smart person, they need fast decision, fast communications, accurate communications or accurate decision. So these are the some of the key points: accurate, fast, and complete information. Okay. Correct information, or you can say actionable information, on which you can take some actions. So based upon that, existing grid is partially smart, or you can say fine, okay, but not the expected way it works. So most of the communications in existing grid is to the utility persons or utility or organizations. It is not to the customers. So you can't expect anything from customers. And it was happened from more than 100 years, and it was going on, and they were trying to solve the problem of power deficit, supply deficit, and then other infrastructures. Finally, they concluded that just working on supply side and delivery side not enough. You have to take the consideration, or you can say some support from customer side. Then only you can solve the problem, and then only you can find a sustainable solution. So from more than 100 years, they were solving one side problems like supply side, but not considering much about demand side. Of course, some demand side management and so on they were doing, but that was not enough. So now they want to take customer also as a part of stakeholder. So of course, utility people think customers are part of problems or source of problems, but now same customers now uh, uh, they think that or thought that they would be the part of solutions. Okay, so now you can see how same customers would be the part of solutions. So it means all will be now stakeholders, active stakeholders. So this is electrical infrastructures which is already there, and just have to add the intelligence infrastructures. Again, I am repeating, it does not mean there is no intelligence infrastructures. There is a very basic, very minimum level of intelligence infrastructures which is just confined to the utility people or utility service providers. Okay, it not connect to the customers, which is the main missing point. So now they are adding more intelligent infrastructures which can provide two ways of electricity and information flow. Okay, so that's the intelligence infrastructures added, and then you get a smart grid. So it become a grid. The same grid becomes smart. After becoming smart, what you are going to get achieve. Okay, making smart means you have a smartphone. Okay, so after getting a smartphone, what are you supposed to do? Of course, if you just want to do texting and calling, then I think traditional phones are enough to do that one. So by smartphone, it means you have to do more tasks and multitasking. So that's what is here. So after becoming smart, you can derive the demand response benefits or demand response and dynamic pricing. So what does mean demand response? Demand response means in existing utility model, they mostly use the DSM, means demand side management, means they replace the appliances or devices with the efficient one. Okay, so that's the demand side management. But you know, also one point more I would like to add here. Until last century, most of the focus was to add more coal power plants, gas power plants, hydro power plants, nuclear power plants to increase the supply. But they found demand is increasing, and still they could not find more supply. Of course, the developed countries have enough supply, but shortage of fossil fuels and pollution, or you can say climate change, or you can say emission, greenhouse gas emissions, created another problems. So now focus is how to reduce the greenhouse gas. So to reduce the greenhouse gas, they are trying to go more lower emission side, or emission lower emission energy sources, low emitting energy sources, and are no GHG emitting sources. So that's the renewable sources. So of course, renewable sources are many. Biomass is also renewable. Hydro is also, especially small and micro hydro, considered as a renewable. Big hydro, in technically, you can say it is a renewable because it does not emit any GHG, but the construction of dams and displacements and ecological, and you can say those changes because of dam are all part of, if you consider as a holistic picture, then big dams or big hydro projects are also not considered as a fully renewable. Partially, you can say renewable. So so in renewable, you have to understand there are two categories. So one is you can control the generation fuel. So you can control, increase, decrease the output of generation as you wish. But second category renewable is you can't control fuel or their output. For example, solar and wind. and ocean energy also up to some extent it is there, not to be controlled. So now the renewable sources which has a controllable characteristics, they are in limited in nature, like biomass limited, hydro limited. So those sources are not enough to supply our demand or meet our demand. So we are going more on the other variable. So we call it intermittent or variable renewable sources, which are no fuel cost, unlimited. So no geopolitics issue here in wind and solar. Okay, of course, other hydro has a geopolitics issue, and of course, biomass is also related to the some extent biodiversity. But solar and wind, there is no literally no geopolitics, nothing, no issue. But they have issue of controllability. So adding more generation renewable side, and though they have a uncertain, so it means you have to change the demand if they are not available, otherwise there will be load shedding, load curtailment. And how to change the demand? You have to go for dynamic pricing. Of course I will talk more details about these things, so let's move. uh, so far, or you can say until last decades or these decades before, most of the centralized generations were considered because they were easy to handle and manage, and small generations were not easy to handle or integrate in the systems, so they were not used, being used. Now, because of the new technology, they can be used, so you can have a better energy security. So like biomass and those small micro hydro or even solar PV, wind and so on. So those small sources you can now integrate. So you have a better energy security compared to the earlier centralized energy security. Also, like our body, okay, you know our body have a self-healing characteristics. Same way, intelligence layer in the smart grid can provide some self-healing property. Some small problems can solve automatically without human intervention. Okay, so that property will be there. And wide area protection and islanding means you can control and monitor wide area, not in a small area. Also, since you are able to get the real-time data or better, or you can say more close to the real-time data, so you have a better asset management plan, or you can say asset information, so you can plan how to utilize better way, and that's improved the overall efficiency of the asset. Yeah, you will know now real time informations of voltage, currents, power, etc. So you can analyze, use the computing power, and then you can analyze in real time what is changes in the solar, wind, or any load or so. So what will be impacts on the systems, and you can analyze and you can prepare for the action plan if something happened. So that's you I told in beginning, okay? So you have to plan in advance actions as per perceived contingency issue. So you have to analyze the contingency, expected contingency in advance, and you have to also plan the actions for those contingency, and you can keep in a queue, and if anything happens, then you can take actions. Also, it create a lot of, or you can say many level of energy markets. Like now, if you have 100 watt solar PV panel and you want to sell in markets, you can't sell because it is mostly you can say suitable for large generation plant. Okay, but this can create energy markets at any level, 100 watt, 50 watt, even load. I don't have generation, but I can reduce 100 watt during peak demand. So I can sell in market that. Reduction of reduction of load is also equivalent to increase of generation or having generation. So reduction of load or adding generation, both will be treated as a same, and it can bid in market and they can sell and buy accordingly and get the incentive. So basically, you have to share the information and continuously you have to optimize. It means your computing and modeling, and of course model will be there, so you have to model and then compute the for the solutions, and then you get the intelligent response. Yeah, Sasri,
Sir, it's fine,
is it
sir.
okay?
Yeah,
So
it's very clear. It's very clear.
any questions from audience? I don't know, I am going little technical, or they are able to get it. Any questions? Any
Participants can
clarification?
give the comments. Any concern or anything? Is it okay? Shall we go ahead? Participant side, it's okay.
If you have any questions or queries, you could type in the chat box or you may unmute and ask.
Okay, sir. Sir, you can continue. They will put up the question in the chat box.
Okay, so yeah,
And I will read. And I will read in
okay.
between. Okay.
Okay, good. But yeah, I feel like sometimes look like no response from them. They are there, or they are just
Okay. I'll take care, sir.
okay.
Sir, they are responding.
Okay.
Correct.
Yeah. Okay, sir.
Any question they understand?
Yeah.
No, they are saying that they are okay with the session. If they're having any doubt, they will type it in the chat box. Then I will read for you.
Okay. Thank you.
Okay.
Yeah, so based upon this, let's now define the smart grid. So definition of smart grid is like a new concept of electrical network which can intelligently integrate the actions of all users connected to it. Now you see, users are not only generators or transmission and distribution company. Consumers are, I mean, they are also users. Not only consumers, also generators, transmission company, distribution company, and many other service providers. All will be the users or consumers. Not better, you can say users, and they will be integrated in order to efficiently deliver this sustainable, economic, and secure electricity supplies. So this is in a brief definition of a smart grid. Of course, these things were already there in past also. In a traditional grid also, their focus is to provide economically secure electric supply. But now, from last decade, added sustainable word also. So, a smart grid employs innovative products and services together with intelligent monitoring, control, communication, and self-healing technology. So, basically, I mean, if you see, so far, it was like, generation was following load. Sorry. So load change, okay, load decrease or increase, so generation accordingly decrease and increase. So basically generation follow the load. Now the idea in a smart grid is completely reverse. Okay, load will follow the generation. So now generation, because of solar, wind and so on, if any changes happen, either decrease or increase, so load will be accordingly increase or decrease. Is it clear?
Okay, sir.
So whole idea just in smart grid you can think of. In traditional grid, what are the major changes, okay, for a layman person? In traditional grid, loads vary, so generation they vary accordingly to match the load and generation. But in this node, applicable, or you can say suitable, or you can say workable, because of now you have more and more variable renewable sources. Okay, I will mostly talk later. VRE means variable renewable energy. Okay, So, and those are solar and wind. Most of them are only solar and wind. So now, because you are adding more and more solar wind, so they will fluctuate as air radiation change, wind speed change, so they will fluctuate. So load should change accordingly. Okay, that's what all about this is going to happen. So if you talk about this in this case, so if you sorry. Okay, so if you see this one, so the aim is to provide, what is the aim of the smart grids? Provide important changes in order to join new and alternative energy sources, reducing the traditional fossil fuel based generation, improve the island sustainability. Island sustainability means basically you can see the if there is any issue, so they can isolate part of the grid and they can operate load and generation in that part of the grid without affecting other part of the grid. So that's island situation. So rather going a whole grid blackout in some unexpected scenario, so now smart grid will be able to isolate, split the main grid in different small grids, and they will be alive or supplying the power, and later they can easily reconnect it. So not expecting full blackout. Okay, so and they can use different sources of energy in that island, maybe waste to energy or solar and wind or battery storage in electric vehicles and so on. So they can supply in that island and increase the intelligence and automation level, making the electrical system capable of dialogue and interaction with the needs of various agents integrated within it. Means they will interact, dialogue among the different agents, means generators, transmission company or distribution company and consumers. So all they will dialogue, okay, where is what and how to do. It will be like share market, okay. Okay, so if you see that this will be the different interoperability layer. So you have a component layers where physical components will be there. You can see the generation, transmission, distribution, distributed energy resources, and customer. Okay. Then you have a communication layer. You have a different protocols. Then you have information layer like data model. Then you have a function layer. What are the functions of those you will get from these aspects? Then you have a business layer, means what different aspects you want to, what businesses will be there. So this will be the different layers and they have to work together. So if you have a solar PV or wind or energy storage, then you can have a bi-directional meter which measure the power energy, how much you sell to grid and how much to buy from the grid. Distributed storage like electric vehicles, or you can treat as a distributed storage. Dynamic pricing means price will be no longer constant like what we have now. So mostly we have electromechanical energy meters which just measure the kilowatt hour. It does not say which time what consumed. So price is fixed. So now you have to have a dynamic pricing like share market, or you can say day of market. So price change, so bill will change. So if you during peak period price will be high, so if you consume more then you will pay more. Smart appliances that you have to use smartly, means when there is a high price maybe you don't use, like washing machine, cloth dryers, irrigation pumps. So you have to add some smart devices so you can instruct the signal if price of electricity is high, they should not use. unless it is very required. If price is low, they can use. Energy management systems, how overall your house energy management or building energy management or community energy management or utility energy management will be there through this one. And of course, sensors and networks will be there for the ICT. Okay, so these are some of the mostly power devices. I'm not talking ICT devices, mostly it will be separate. So meter will be smart. It measures the every intervals, maybe 15 minutes or 10 minutes or 5 minutes. It depends upon the what you can do. But keep in mind, as much as intervals, then that much data storage and management and those all issue will be there. So you have to prepare accordingly. So you see deployment of variable renewable or you can say generation technology. So you have a you can say even how this is common hub, different sources, different users, bulk generation is also there. Just you have to add a smart meter and a smart router, which ICT device, and this is smart meter means energy meter. So it will connect and all will be through a common hub. So this is a smart grid. Okay. So every information will flow from one to another and they can take decision accordingly, like how you take now. Okay, like in real time you can have a monitoring in building or your house. So how much you have a demand, how much you can produce if you have a solar PV or so net demand. If you see the demand is high, price is high, so you can reduce, let's say this air conditioner. So if you raise the thermostat setting 1 degree upper or increase up, you can save around 6% energy. So if it is using 24 degree, you can raise to 25 degree. If you are using 20 degree, raise to 21, 22 degree. So you can reduce the demand. So your bill will be reduced. So this will be useful for customer level, building level, and so on. Also, it will affect our lifestyles because a smart appliances you can even communicate. So by that also you can save the energy. Like if you come from office, you go to home, you see what are the stuffs you need to buy from markets. Then you see in fridge and storage, and then you go back to market. But if you have a smart devices, then you just communicate. Inside you can see how much stocks are there, vegetables or drinks or whatever, and then you can buy on the way, going to home. Okay, from office to home, you are going on the way somewhere. You can go supermarket or departmental store and then buy stuffs and go home. So you can save those things. Even you can have a better healthy foods because maybe barcode and so on can be happen. So you can scan and then fridge will tell you. You can connect with your mobile and then you can say see that how much expiry date or what is the status of those foods. Even washing machines can connect with your smart device and you can instruct remotely when to use, when not to use, if prices of electricity is different. Any questions?
It's fine, sir.
Okay. Okay. So that's what little information about smart grid. Now you see the challenges of, or you can say rationale for smart grid, why we should go for smart grid. So in one projection or another projections, everyone predict that our fossil fuel will start depleting from mid of this century or next century or end of this century. So you can see this is the total supply and they will start depleting, reducing. Okay, this is global. Okay, but if you see total demand is increasing exponentially, So already gap between total demand and supply started increasing or widening, and we expect in next 50 years it will be double. Means double means what is we have supply, demand will be 2 times of that. So this gap will be filled by what? So you have to fill by alternative sources. Okay, so you have to find some alternative sources. Also, smart grid will provide societal benefits, financial, technological, regulatory, and policy. So this is basically the 4 dimensions here. So it will provide different aspects, benefits. Also, people go for a smart grid because of from utility perspective. If you look at, they expect it improve the efficiency. Also, they can integrate more renewable because current power grid mostly have a 15 to 20% backup supply or surplus capacity, and which are of course not very fast, because any generation, as I mentioned, if there is a deficit or a surplus, it will reflect in a millisecond, microsecond. But none of the generation is able to shut down or start in a millisecond. Even fastest is like diesel generator, or you can say those things. I'm not talking about power electronics connected battery storage. They can be in a fast, maybe a fraction of second they can be connected, but we don't have that much of battery storage. So if you talk about new source, diesel generator or gas turbine or coal or nuclear or hydro takes 5 minutes to start, and coal take 12 hours to 24 hours to start. Gas turbine takes 15 minutes to 30 minutes to start. So none of the sources are very fast. So if solar wind reduce, so you don't have backup unless you go battery. So battery cost is almost like same what you have generators. So it means it is redundant or expensive options. Also, around this much people say around 30% plus enabling new products, services, and markets are the drivers for the smart grid. Also, they say it improve the reliability. Also, they say it improve the asset utilization. Okay, so different aspects they say for the smart grid. If you talk about, of course, each country has own, but if you see about EU GHG emissions, they are targeting to decarbonize power sector fully by 2050. Okay, it means this is the power sector, and as I mentioned earlier also, but you can see this is one example. This is this diagram show load is dotted line and wind power availability is a solid line. Sometimes you see these periods wind is able to meet the total demand, but rest of the period not, and even sometimes it goes zero wind availability. And this is, you see, the demand is fluctuating from 2000 megawatt to 3500 megawatt. If it is zero, from where you will get that much 2000 or 2000 or 3000 megawatt power? It is not possible battery. So you have to go some alternative, and that's maybe demand response. Of course, you can't shut down full grid. This is just talking about wind. But if you have a solar, you have a other traditional sources also, you have to think that suddenly not possible to go all remove the coal. For that, you have to prepare enough other sources and options like storage and other alternatives. Then only you can go for 100% renewable. That's far away, but few places, few microgrids, few islands, they have tried to have 100% renewables. But storage is a big factor over there. Then this is solar, another case. In one case, you can see here, 81% drop in 5 minutes solar irradiation. So this is just 8 megawatt solar farm. So okay, fine. But suppose in India now they are bringing a 2,200 megawatt solar farm. If that 2,200 solar farm reduce 80%, what will happen? Okay, you can understand almost 2,000 megawatts gone. Then what will happen? 2,000 megawatts bringing suddenly in 5 minutes means 2,000 megawatts hydro plants we don't have and we can't have, because these plants, if you don't run, don't produce, they will be like a white elephant. Okay, so you can't have a just for backup. So these are the issues. So better what you can do, can you reduce 2,000 megawatts demand so you can compensate without having storage and other generations. So that's all come from the smart grid. Okay, same things here also. It will be you can fulfill or you can say get or you can solve this problem by smart grid by reducing demand. Of course, you can't reduce all demand, but you have to find multiple solutions. Another big problem in power industry is asset utilization. Because demand is like you see, even if you in this curve, you see demand is how this is peak, then peak off, peak, peak off. So this is not continuous demand. So it means you see your generation and transmission distribution capacity should be 3,500 megawatt, but average maybe it is around 2,500. Maybe average is 2,500. So what does mean? It means you have to have a 1,000 megawatt over capacity in terms of transmission, distribution, generation, all. So average is 2,500, but peak is 3,500. It means you have to over capacity and not using all time. So that create big problem. Like if you see here, more than 25% of distribution asset means the transmission and distribution infrastructures, and more than 10% of generation assets are needed less than 5% of the time in a year. It means it is like hundreds of billions of dollar investment which will be redundant, or which are redundant, which are no use. So can we avoid these redundant investments and move for the smart grid investment? And so you can make the demand flat. Of course, it cannot be a linear flat line, but it can be slight fluctuations, so it's quite close. So that will reduce a lot of issues of over investment in infrastructures and also variations. So this is what expected that smart grid can help to do that one, flatten the load. Because of that, you see the frequency how vary. Okay, so you can see the 50 hertz. So there is some big load connected or big generators disconnected. So frequency start dropping, and this is the free fall. You can't do anything in this period. Okay, fraction of seconds also. Then you take action. Then again you restore back the frequency. Okay, so how reserve, fast reserve, reserve. I'm not going to talk more about that, but it is like you can say your thermal generators capacity is 1,000 megawatt, but you are running at 950 megawatt. So you are producing steam 1,000 megawatt equivalent, but not using 50 megawatt. You can say in a then rate of change of frequency will be very high for same change in the load or generation. So that's the telling here. Okay, so if you have a system, means you have a less mass rotating type of generators, then you have a high frequency here. So this is one, but there is a solution. I will tell you. Okay, this is a voltage problems in grid codes. So you can see if there is any fault, then in this is millisecond. You see this is second, so it means millisecond. they have to bring back the voltage to normal or at least within the 70-80%. So different country follow different grid codes. So if there is any faults, they have to bring back the voltage. If you have a penetration, so reserves requirements are increasing. This is the you can say fast reserve, spinning reserve. So it is more or less constant. This is the wind sources. X-axis is wind power production in megawatt, and this is the reserve. How much you need? How many megawatt reserve you need? So if you add more wind or solar, so fast reserve is more or less constant. It is related to one big power plant's size. But slow type of reserve, this is 30 minutes backup. This is maybe 1 hour. This is 4 hour reserve backups. So you can see the slow reserve backups need to increase if you add more VRE. Okay, so these backups cost a lot, very expensive. Okay, it is maybe more than or equal to generations. So rather going these reserves, maybe go for demand response. So because of those reasons, photovoltaic and wind capacity factors, no dispatch, you can't dispatch easily unless you have a storage, and ultra fast ramping requirements because irradiation wind speed change very fast. So if you have a 20,000 megawatt solar or wind, so you have to have a ramping of those compensation like 400 to 1000 megawatt per minute drop or increase. Also LVRT, low voltage right throw capability, what I told here, you see, generators should have able to operate in this region above, not below. This curve below not operable, no operation, but above these curves have to operate, need to be operated. Shashi, is it okay?
Yeah, it's fine, sir. It's fine.
Okay.
Fine, sir.
Any questions from audience?
Questions from audience? Any questions from audience? You can type in chat box. Okay, sir.
Okay.
Oh, okay, sir. We can go ahead, sir.
Okay. So because of these reasons, we have problem from operation side. So what they do, as I mentioned, most of the existing sources takes time to start and also they take time to shut down. So solar and wind are very easy to start, or you can say cost of starting is also high in those traditional sources. But solar and wind starting cost is very less. So if suppose there is a demand in night time, you know, nighttime low demand, and this is the must run level because as I told you, coal power plant takes 1 day to start, so they can't switch off in night and start in morning, so they have to keep running all time. Some run of river type of hydro projects also they have to use it because they can't store. Also, some power plants, nuclear, you can't shut down and start, which takes month, several month or year to start and also to shut down. So most of those generations which are expensive to start and shut down, they keep to run all time. So in night time they run also those generations, and like gas, maybe they can shut down. And suppose if there is a wind speed available and they have a surplus power energy in night time, what to do? You know, it will raise the frequency. So it means they have to curtail some generation. So they have two choice to curtail. One is wind, another is the must run generations. So if curtail must run generation, then again in next morning or 1 hour, 2 hour later, if no wind or no, then they can't start. So they will not curtail those base generation. So they will curtail the wind generations. It is easiest way to keep the cost low and also keep the reliability at high level. Then what is use of renewable? So if you have a smart grid, then During this excess generation, just send the price signal, reduce the price further low, and then sensors and those devices will detect and they can start using for some other applications which are switched off during daytime, like let's say irrigation pump. So the farmers can use the irrigation pump in night time when there is surplus power and low price. Or you can use the washings or cloth dryers or maybe other industrial loads where like fridge, ice, like cooling or heating loads. So they can make ice or they can heat up the water and so on. So I mean different loads which can shift from one time of the period to other time of period. So they can use during that period, or you can store in your electric vehicles or so on. But these all things only possible once you have smart grid options, means intelligence layers. Okay, so that's then you can utilize. Otherwise, if you don't have that option, then it means it will be curtail. This wind energy will be curtail. And just I give an example. I will show you later also in China. 2 3 years back, they were curtailing like 15 to 20% wind energy because they don't have a uh, demand or they are not able to use it. Yeah, this is you can see here. Okay. Another problems as you are going to use more and more renewable, fluctuating type of sources, they will create a lot of voltage problems, power quality problems. And power quality problems is a big problem as we are going more sophisticated industrial era, or you can say sophisticated applications. Like you see, just simple lighting and motor load, maybe millisecond outage, interruption of power will not have a problem much. But computers, digital clocks, all will have a problem. They will shut down. So a lot of losses, 80 billion, here 50 billion, and so on. So basically half of all the computer problems and 1/3 of all data loss can be tracked back to power lines. So these fluctuating sources will create a lot of problems to the loads. So what to do? So you can move the loads. You can see this is the load curve, okay, actual. So you can switch, you can plan what storage, what electrical vehicles, what movable loads, what business, industry, private homes, how can utilize so that average load is constant, or you can say very close to flattened line, and efficient, you can say efficient, no doubt, and then economical. So those are the things will be happen. So basically smart grid will try to flatten the load demand or load curve. Okay, if you are able to use those by smart grid, then you can you see just one proposition of in New York State. So here telling if they use smart meter and smart grid technique, then they can shave by reducing this peak demand. You know, another flaws or you can say disadvantage of this peak demand. These peak demands supplied by or met by the most of the expensive generators, which are not economical to run in terms of money financially and also GHG emission. So they consume, maybe their cost is very high and also they produce more GHG emissions. So they keep for that for peaking power plants or for peak periods. So during that period, if you can avoid the 100 megawatt peak demand, then you can save $8.5 million for avoided capacity value from generation, transmission, and distribution. Also, 100 megawatt usage moved from top 20% of hours of off-peak periods, which will reduce the bills, or a $5 million energy savings. Conservation, if you reduce those peak usage, then each 100 megawatt reduced usage could lower carbon emissions by 500,000 tons per year in New York State, which is equivalent to planting 68 million trees or taking 71,000 cars on the road. So these are the other environmental societal benefits, okay, of the reduction of peak demand, and which is only possible by using smart grid technology. Also, you know, the fluctuations in the grid supply side, if there is there, so it means you have to balance from other sources, and balancing cost is different and it is very high depending on the country. Like Germany, you can see if you use this is base case, means no variable renewable sources. This magnetoclar, which means 10%. Wind, or you can say, yeah, wind, 20% wind, yellow. So in Germany, cost of balancing is this, but Norway, Sweden are less. Region is Norway mostly have a 95% hydro power plants, and Sweden also like 50% hydro and rest nuclear. So I mean, they can supply from hydro, so they can easily meet with less cost. But other cases like Germany and Denmark, they do not have a much hydro, so their balancing cost is high. So these are the other implications of peak demand or variations. Yeah, I'm not going in much details. In future, we are talking more and more renewable, but mostly VRE means variable renewable sources. So to integrate or to use them, you have to have a more flexibility in the grid, and flexibility will come from the smartness of the grid, smart grid. So you can use that flexibility, then you can integrate more VRE. Yeah, just a few in technical terms, I can say, especially in computing power. So, you know, in power grid, this is the dynamics or response in milliseconds, 100 to 200 milliseconds, where protection and local controls needed. Then more than 60 seconds, like wide area monitoring and control is SCADA EMS, you see. So it becomes static here, SCADA and EMS. But this is for traditional, but in future or in smart grid, no more static. We need all very fast computing, and then you can manage better way. So in smart grid, what we expect, GPS synchronized phasor measurement units will be located in a power grid at different locations, and they will be tagged with the GPS so that time synchronization is same at every place. Data will be taken from different power plants or different substations, and then those data will be given to centers through SCADA EMS or this VAMS control, and they will monitor, control, and take actions accordingly. So it will be very fast, basically. Okay, so it needs also soft computing to speed up. One case you see in existing today's grid, SCADA takes seconds, state estimation takes minutes. Means computation of the unknown states are very time consuming. Then contingency analysis also takes minutes. So these are all computational issue, okay? And then operator, if violation, then operator take action. So it is more like static. Okay, so it is a very, you see market operation takes hours. So basically very slow operations, and then not better utilization and fast response you can get. So that's why you can't utilize more VRE. Okay, you can't utilize more VRE. So to utilize more VRE, you have to speed up these all process. Okay, so for that you have to design the wide area monitoring systems, like computational time plus communication time must be less than response time of the system dynamics. Then only you can use more VRE, and that's what purpose of smart grid. So by that you can have an online real-time monitoring and state estimations, which can realize one state estimator run per cycle. Provides opportunity to peep into electromechanical system dynamics, means you can see the electromechanical dynamics faster. You can better way control. You can improve the other informations. You can improve the other things. Accurate measurement of transmission system data in real time. So by that, if you see, it becomes fast time. Means here, these things will be scatter and phasor measurements in sub-seconds. Dynamic state estimation, sub-second, and other dynamic online contingency analysis, transient stability analysis, voltage stability analysis, all sub-seconds. So computing become very fast, and of course ICT and those things. So it can take in a faster more decision, and which will be very much good for better utilization. So that's what computing power here will help. So now electricity systems will be taken as a, you know that, yeah, Sasi, 20 more minutes. How much more times I have?
20 minutes, sir. We can stop 5 minutes early, maybe 50 minutes after we will open up for discussion. So you can
Okay,
continue for 15 minutes.
15 minutes. Okay.
Yeah.
Okay. So, okay, thank you. So this is the, you can see that this is the electricity systems which is working for battery level, household level. Then you can go for micro mini grid level, then you can go national grid level, then regional interconnection. So this is also a way how to create a isolated microgrid which are physically connected but electrically maybe isolated. And it can be electrically connected, as case may be. So next level is home level. So we expect home will be like you have a more renewable sources, you have of course communications, you have electric vehicles, you have smart appliances, you have HVAC means heating, ventilation, cooling devices will be smart, so you can control better way. And also you can coordinate other services like demand response, and then also so other services means you see water, gas, heat meters. You can combine same smart meters can measure, I mean it will be combined together, so same customer care or customer service center or billing center can process bills for water, gas, heat, okay, electricity, all. So same billing possible, same desktop or desk. So it will also leverage the other applications. Yeah, you can see your real-time bills, and which has a very much impacts on your behavior changes. And you can see how much using when, what is your neighbor's bill, and what is average neighbor's bill, and what is your bill this month. So you can target fast saving. So this display will be very important for changing your behavior. Just an example, in telecom industry, most of people switch to prepaid mobile. Why? Simple reason is they want to see the bill. Now you can see in postpaid mobile also you can see the bill, but earlier in beginning only they were able to see after 1 month, and they could not see how much bills will come before, and they afraid, and then they switch to most of them in prepaid, and that's only to see how much they are spending. Same way, if we see the energy meters every day, how much I spent yesterday, how much I am spending today. So many people will avoid unnecessarily use, like you switch on the TV while you are not watching, you switched on the light or fans but not using. So if energy meter will be showing your bills like in real time, then you will worry and you will then avoid those unnecessary inefficient operations. So these things will be very helpful in the improving the energy access. Okay, how overall changes will occur in a smart grid? So today there is no limited interaction, that's passive customers. Then you have enabling technology to give customers new informations. Means you add the smart or intelligence layer, so you inform customer what type of generations now using, what is the demand, what is the load, generation, and what are the components fail or plan, and this and that. Those informations if you provide to customers, so customer will think accordingly, and then enabling services you can use and then provide the incentive, means pricing. So this is inform customer. Then customer will take action or they will change their behavior, and that actions will be helpful to the grid, and then customers make investment. If these things look like helpful, then customers start investing. Like they can have a more battery storage, they can have a more solar PV, they can have a more other devices which can improve the energy consumptions. So that's then become customers become the part of a smart grid. So this is the last level one to achieve, but still there are many steps need to do which are far away. Yeah, utilities are being here or here, okay, or here, okay. So most of the cases are pilot projects going on, of course many implemented, but most of the cases are here, okay. So still far away to go. Of course it is very expensive business, it is not simple, I will tell you later. Okay, these things I am going skipping because of the time. I am not going to discuss. Of course, electric vehicles will be a big issue because of high demand, but they can be also a good incentive in terms of they can generate power. What battery store, peak period they can supply back to grid. Okay, so these are all details. Hybrid electric vehicles. This is plug-in where you can charge from grid. Here you cannot. This is purely battery electric vehicle. You see the size of battery increases. Then you have extended range. A small engine is here, and then you have a fuel cell vehicles. So these are the different types of electric vehicles. I'm skipping these things. Big demand. Yeah, this is the in energy storage. In future, you have more cars, more electric vehicles. So you can see the lot of energy storage, like around $5 trillion energy storage markets. Yeah, this is one example. Compare if you use electric vehicles and you connect to the grid, vehicle to grid. So you have a better economy, so you can earn money. Okay, so you can see the net cost is $319 per month lease cost for IC sedan, but if you buy electric vehicle, then net cost is $100 per month. So it reduce. Initial cost is high, but operational cost is very low, and also you get incentive because utility can use your battery storage for their storage purpose. Use. This is different market purpose. Life will also have impacts. This is virtual plants, means you have storage, load, and so on. You can create a virtual power plants. This is the dispatch model for the virtual power plants. Benefits of smart grid, no doubt, new jobs. A lot of new jobs will create in different sectors. Innovations will be there, and other lower cost will be there. And other broader societal benefits like emissions reduce, and then other health issue will be better. Key challenges, again I'm going faster. Key challenges are regulatory challenges, not easy. Many technology have to remove from the systems, which is not easy. So you have to create a clear cost recovery policy, how to replace the existing technology. And financial perspective, huge investment, huge benefits. Okay, so these are the all challenges and have to tackle it, but it does not mean you have to go at large scale. Better you can find in a small case and go step by step. Then you have a technological challenges. It is very much, the instrumental, huge amount granularity of control, market driven, safety and privacy of consumer data. All are the issues. Your behavior can be tracked. What time you are sleeping, what time you are in bedroom, what time you are in washroom, what time you are in living room, what appliances you are using. So these will be tracked. These are the some issues of that. So from your energy profile, consumption profile, they can track. So they here big data and data analytics can track your behavior. That can be that used for different other purpose like insurance, health insurance, other market. Information security, no need to say, already a lot of issues are there. Challenges in implementation like integration challenges, adoption of service-oriented architectures, web service enablement of the legacy apps, handling wide variety of non-XML data formats and so on. So the human challenges. It is not just power engineering. Please keep in mind this power engineering is one, but electronics, power electronics, economics, finance, system architecture, IT, software, communications, project management, environmental engineering, and many more disciplines required for a smart grid. And design challenges, large number of small sources and storage incorporating two-way. So far grid is mostly one-way electricity flow and information flow, but if you want to flow from your house to grid, then many protection and devices need to be incorporated, or you can say have to change. So a lot of changes are challenges are there. Okay, so conclusion, here you see a lot of research scope and works to be done to implement at large scale. Still, there is no clarity when whole world will be available or implement full smart grid. It may be takes 20 years or 10 years or 20 years or 30 years, not clear. It is huge investment. So very difficult to say. So slowly can go, no need to go at large scale or whole scope level. Okay, so these are different age of research going on. Very much. Yes, Sasi.
We'll open up for questions. Participants, you can ask the questions.
Thank you, sir.
So, sir,
If you
can
have
you
any
just brief?
questions or
Yeah,
queries,
Sahla, 1 minute. Sir, it
if you
will be
have
good
any
if you
questions
can.
or queries, you can type in the chat box or you may unmute and ask.
Okay, sir, if possible, just brief the research possibilities because diversified community is there.
Okay. Okay, you see, policy and regulation. Actually, you can't work with the existing regulatory body, I mean, the policy and the regulations. So you have to change because in the existing one, you have a countable number of generators and entities or utilities, okay? You can count on fingers. But once you integrate customers, so they will be also entities. Of course, their scope is size is small, but each customer will be an entity or utility. Okay, so it means millions of those utility will come in the picture or in the market. So a lot of conflict of interest will be there. Their management, the all will be issue. So a very dynamic and policy and regulation have to be there. And as I mentioned, a lot of devices maybe have to remove. Let's say electromechanical meters, you have to remove. You have to have a smart meter. What will happen to cost of those devices which just installed last year or this year? So you need a very strong cost management, conflict. So those things have to think for policy and regulation side. Okay, then we have a integration of renewables. So it is related to power electronics, it is related to power systems, it is related to the demand side management. So there are many dimensions of this integration issue. Okay, then you have electric vehicles. The transport side also have a How those electric vehicles will be charged, when will be charged? You know, in existing customer, their demand is assumed to be 2 kilowatt. But if you charge electric vehicles, maybe 3, 4, 5 kilowatt demand. So if a customer just buy one electric vehicle, her or his demand increase 2, 3 times immediately. Do we have enough infrastructures, line size, capacity, or transformer, or generation also? No. So we have to think about that, how to integrate those charging, discharging. Demand response, as I mentioned, generation side variations is coming, so you have to change the load side to counter that variation from generation side. Then how to do that one? It is a big things, technological side like ICT, information and communication, and then also you have to have it from customer side, social engineer, I mean social side, how customer will participate, how, what incentive, what benefits should be provided. So you have to design accordingly. Then this is related to power system, reliability, efficiency issue. Those small changes, variations will have impacts on the system operation. So how to handle those variations? Waste management, a lot of e-waste and many other waste will be there. So how to manage those things? Then no doubt, you know, the big data and cyber security will be a big issue or huge issue. So how to handle huge data, management, security issue, privacy issue, all will be there. So how to handle those things. And then of course, how to make resilient grid and disaster proof, or you can say better disaster management approach. If there is a flood or there is earthquake or there is any outages, so how you can manage during that period, grid. So these are the different, I mean, it is not a complete list, exhaustive list, but okay, these are the some different dimension of the research or work to be done in smart grid area. Of course, as I mentioned, ICT. ICT guys alone know what is ICT, but what is expected for from smart grid, they are not aware. So ICT guys should know smart grid functions, what expected from smart grid. Then they can only manufacture or design ICT devices which can work better. Okay, so this is also very important for ICT guys to understand these smart grid issues or applications. Then they can design accordingly. Yeah, that's it.
Yeah. Thanks, sir. Thanks. I think we can wind up.
Okay, so any questions? No questions?
Any more questions? Sir, I think everything is clear.
Okay. Okay. Okay.
Thank
Then
you,
you
sir, for
can go
joining us.
with the
We are
concluding
really
comments.
enlightened with your. Okay, sir. Thank
Yeah.
you, sir, for joining us. We are really enlightened with your knowledge and presence. I request you all to fill the feedback form which has been provided in the chat box. Now we'll have a break for half an hour. The next session is a quite interesting one on smart grid in machine learning, handled by Dr. Venugopalan Kurupat. The session will begin at 12, and please do join 5 minutes prior the session. Once again, thank you and stay safe.
Thank you, sir.
Okay, thank you.
Thank you, sir.
Thank you again.
Thanks.
Good afternoon, sir. Sir, let me start the session.
Yes, you can start.
Good afternoon, everyone. Welcome back to the second session of the day on the topic Smart Grid in Machine Learning. A smart grid is an electrical grid which includes a variety of operation and energy measures, including smart meters, smart appliances, renewable energy resources, and energy efficient resources. To let you know more about smart grid in machine learning, we have Dr. Venugopalan Kurupat, who has taken BE Electrical and Electronics Engineering from College of Engineering, Gundi, ME Applied Electronics from Coimbatore Institute of Technology, and his PhD studies at Uppsala University, Sweden, in the area of renewable energy. He has 13 years of teaching experience and is currently working in Muthoot Institute of Technology. So it is our honor to have you with us today. Let me hand over the session to you, sir.
Thank you. So let us start the second session. I am Venugopalan Kurupat, as I was introduced. I am a BTech BE in electrical, and I'm an electrical engineer. Okay, I've been in academics for the last 18 years, and I have some 6 years of industrial experience. So that is my brief introduction. Okay, so today I think the topic that was mentioned, it was mentioned as smart grids in machine learning. Actually, it is machine learning in smart grids. So we will try to see how machine learning has a place and importance in smart grids, and why you are spending a whole day in your 5-day FDP, why you are spending a whole day talking about electrical grids. Okay, so whenever we talk about big data, machine learning, and other topics, we always think of e-commerce, logistics, manufacturing technologies, service providers, and those kind of areas where you have big opportunities for these kind of new technologies. Okay, so but what we miss is there is a whole sea of opportunity in a area like electrical grids. Okay, electrical grids, as we have seen in the previous decades, or as we see today around us, this is an old type of grid, and there are rapid transformations taking place in the electrical grid, and these kind of transformations are always going to result in very wide adoption of new technologies. Okay, the technologies, new technologies will include communication technologies, it will include IoT, it will include big changes in how customers are integrated into the system. Okay, so we will see a few aspects. I'm sure you have been given an introduction about smart grids. I would still like to spend a few minutes trying to put machine learning in the proper perspective. Okay, so you'll be wondering why machine learning is of importance in grids. So I'm sure the first session has already given you a hint about what a smart grid is and how complex the grid is, and what kind of importance data and data processing and data handling has in smart grids. Okay, so let me start my presentation. I think we are around 35 people, 35 odd people here. It's a very manageable group size. So if you have any problems in hearing me or seeing my slides, or in general, if you want to add something to what I'm mentioning, because we are all academicians, we're all part of this academics circle, so we can always complement each other. You can add some points. Please raise your hand and just interrupt. Okay. So organizers, please keep an eye on the audio and the video. Okay, if something goes wrong, please interrupt.
Okay,
So let me present now. Let me start my presentation. So let me start with a picture of what a grid looks like. Okay, what the Indian grid at present looks like. It is a symbolic picture which tries to convey what kind of a challenge we have in modernizing our grid. Okay, so you can see this site is very familiar to all of us. We have seen this kind of mesh of wires or a tangled mesh of wires running around. And if we have to look at a grid which is growing more and more and more complex every day, and if you have to troubleshoot, or you have to handle that grid manually, like this man is trying to do, okay, you can imagine what kind of a difficulty we will face if you have to control and run this grid in a manual mode. Okay, so this tangle of wires and this mess that we have created because of the large size and unplanned growth of the grid, we have to untangle all this. We have to put proper infrastructure in place. We have to learn how to handle data processing and data learning techniques, and we have to incorporate many new technologies like machine learning into handling a grid of a size that we have in India, and of the geographical size, the variety of geographical features that we have in India. So we have a very challenging task, and machine learning and people from computer science, experts from computer science, are going to be very important. I would like to say more important than real electrical engineers in the modern electrical grids. Okay, so there is a wide opportunity available for professionals in these kind of fields to go and work in electrical companies, big electrical companies, and there is a lot of contribution that these kind of professionals can make in the grid, make the grid better. Okay, so let me go to the next slide. So what is the content of my 2 sessions? Okay, I'm having 2 sessions, one till 1:30, and then we start at 3 and go on till 4:30. So these are the contents that I would like to cover. So I will give a brief introduction about the complexities in the electrical grid, try to put the requirement of machine learning in its proper perspective. Then I will try to highlight what are the different areas where machine learning is required, and wherever machine learning is being planned in the electrical grid control and operation. Then I would like to highlight what are the advantages of using machine learning in smart grids. And then most important of all, I would like to present a small example or a hands-on example, a case study of demand-side management. Demand-side management is a very often heard topic. Right from undergraduate students, you would be hearing demand-side management. So I will give a small example of what demand-side management is and how to do this, how to optimize a customer's load with the help of a Excel worksheet. Okay, so that will, even though the study is a very simple example, it puts in perspective what is the requirement when we take up complex examples of the same kind. Okay, so that I will demonstrate. And then in the last, I would like to show K-means clustering case study for profiling customer load characteristics and what are the implications of that in the smart grid scenario. So I will not go into too many complex machine learning techniques here. But my focus will be to highlight what are the requirements of smart machine learning in grids, and provide you with 1 or 2 examples, and go through all the aspects of that example, the Indian context. Okay, so when I look at this, so we know that India is a very large country. It has a very large population. So effectively, the number of connections that you have will be very large, running into millions of connections. So that brings the first picture into context. You see the sea of wires running, overhead wires running. So the grid size and complexity is very large. The per capita power consumption in a developing country like India is very low compared to the developed countries. But the sheer number of connections that you have is very, very large, highly connected grid that we have to handle. Then we have varied generation resources. In the mountainous regions, we have large dams in those places. And we have a bulk of coal-based thermal power plants. We have renewable energy pockets of wind farms and solar farms. Okay, so we have a very varied generation resources, and the topology. Some areas are freezing cold, some are much above the sea level, some areas are on the sea level. So we have a very varied topology and climatic conditions. So this has an implication on the seasonal load variations that we are going to see in India. Okay, so all these factors add to the complexity of the grid operation and grid handling. Okay, and what is more to be taken into account is we are a developing country. Most of our grid is legacy equipment. If you go around and observe the amount of transformers, it is very likely that you will find 30-year-old, 40-year-old transformers, very old and outdated equipment, very much overloaded. They are heating too much. Their efficiencies are very low. Okay, so you have such legacy equipment, very large transmission losses, again because, okay, so you have transformers overloaded, so the transmission losses are very high, and a very large skill upgrade. Okay, so whenever temperatures, everything is shown in this slide. Okay, so now let's look at what kind of a generation is available. I don't know whether it is a repeat of what we have seen in the first session, but I'll quickly go through this. So you will find on this side you have the green dots, green region belonging to the renewable energy, nuclear, hydro, diesel, gas, and coal. And you find that the bulk of the generation is coal, and there is not much change in that. It has been growing it has been growing in percentage over the years. So coal still forms a basic block of our generation. And you will find the hydro is actually gone down a little. That is seasonal, and it depends on the rainfall. And it also depends on the growth in other factors, other areas of generation. Okay, and you will find a very small increase in renewable energy. So renewable energy actually has been doing quite well in India. We have a 175 gigawatt plan, and that there are aggressive plans to meet that target. Okay, so the renewable energy has been growing, but it is far away from playing a dominant role in Indian electricity generation. So this is just to help you understand what kind of a grid, what is the southern grid look like. So I'm not talking about the whole grid. I'm talking about a part of the grid, central and southern parts of the Indian grid. So a grid like this, if you want to look at it as interconnected nodes and those kind of elements of the grid, then it looks quite complex as such. So if I look at the next figure, if I zoom in and look at the smaller elements of the grid, then it starts to look really complex. Okay, so if I want to do a deterministic or a type of analysis on these kind of grids, then I know that it is very complicated. The kind of nodes that we have will run into thousands and lakhs of nodes, and if a proper deterministic analysis of the grid and operation and control of the grid based on a deterministic analysis is going to be very difficult. Okay, so we need software tools without which we cannot talk about control and operation of this grid in any meaningful manner. Okay, so that is what I would like to emphasize by showing these pictures. Okay, and this is only the southern and central part. The remaining parts of the grid are equally complex. Okay. So let me go into distributed generation. So whenever we are talking about smart grids and we are talking about machine learning in smart grids, so I am compelled to bring in a distributed energy generation into the picture. even though machine learning in grids, in electrical grids, as such, in the conventional grid, it has enough scope. But the moment I add distributed generation, the requirement increases manyfold. So what is that complexity that is added by having distributed generation? So let's look at that. So we find in the picture here, we find that this is a conventional mode of electricity grid. You have a central plant here, and then you have the power flow. The red arrows show the power flow. Okay, so the power is flowing into a substation, and then it is going to individual housing colonies and things like that. Okay, so this conventional grid has to handle only power flow in a single direction. Okay, that is what I would like to emphasize here. So in a conventional grid, you have generators on one side and you have customers on the other side, and the power is always flowing from the generator, the big generators, to the consumers. Okay, and if there is a problem in any part of the grid, then the power flow is supported, the protection is supported by directional relays, and it is always easy to handle these kind of grids. Okay, these kind of networks are easy to handle. But the moment I have distributed generation, okay, I'm having distributed generation now, and if I have that, you can find that on the houses here, you have solar panels here, so you have a kind of a distributed generation. And now the control that was available in only connected to the central generating station, you can find one brain here, and that is the blue lines are the communication and control lines. Okay, so the blue lines are going from the power station here, and the control is going to all these consumers. Okay, but the moment I have distributed generation, I am going to have control not only in the main generators, I am going to have control operations or generation control. These kind of control aspects are going to be distributed all over the place wherever there is a generation. And another thing is the power flow now is bidirectional. Okay, the power flow is not unidirectional anymore. You will find that the control network is larger, it is more complex. There is an aspect of distributed control in this picture, and there is also an aspect of bidirectional power flow. Predominantly, it is still from the big generating station to the consumers, but addition of local generating resources are going to have a bidirectional possibility in power flow, at least in some areas. Okay, so that complicates the grid manifold. If you go into an analysis of the control and operation, you will find that there is a manifold complexity increase in these kind of grids. Okay, so are these smart grids? Now the question that people ask is, I have not come across any smart grids until now. I'm sure many of you won't have come across any smart grids in actual practice anywhere. So the question that people ask is this something that is far away in the future? Okay, will I see it after 10 years, 15 years, 20 years, or a few decades after? So what is the status of smart grids? Is there any smart grid operational in its full sense? Are there any plans to introduce smart grid in India? Can I see some smart grid in operation in the near future? Okay, so just to answer that, just to answer this question, Bangalore Electricity Board, okay, electricity company, is starting work on a smart grid, and they have a target of 2027. Okay, so this is the flyer put out by BESCOM, and they say that the actual transmission and distribution losses in their grid is more than 30%. So they have to cut down that. They have to reduce power cuts. They have to manage peak power and demand response, and they expect by that time to have a large electric vehicle in their connected to the grids, and how to manage the charging situation of these electric vehicles. Okay, how to integrate renewables and distributed energy generation efficiently and reliably into the grid. So these are some of the objectives of a smart grid that BESCOM is putting out. So a smart grid vision for India is very much practical, and it is very very real. Okay, and very soon I think we'll start seeing some indications of this line of work. Okay. So when we talked about distributed generation, what is actually the problem? I said whenever I introduce distributed generation, the complexity of the grid and the complexity of the control goes up multiple times. Okay, so what is actually the problem with the distributed generation? Apart from its variability, the distributed generators like wind power and solar power, there is no guarantee how much power it will generate over a period of time. That depends on the climatic conditions, the wind speed, the solar irradiation that is received in a particular area, and all that. So, and it's a highly varied kind of generation. Apart from that variability, what is the other complexity when we have small generators connected to an established grid? Please, I would like to emphasize that when I have small generating stations connected to an established grid, what are the problems? So every DG, every person who is setting up a solar plant or a wind farm wants to optimize their revenue. Okay, so what that means is they would like to pump the maximum real power that they can generate into the grid. Okay, that is their objective. So the objective, this objective itself causes problems, because they would like to operate in unity power factor. They would like to convert all the generation into real power and pump it into the grid. No DG wants to take up any part of fault currents or reactive power support. Okay, so no DG wants to do any of that. The basic reason for that is many of these renewable energy sources have a front end inverter converter section. So they have a power electronic front end, and you know that overload capacities of converters is very limited. Okay, so they don't want to take any fault currents, they don't want to have any part in fault current support, and they don't want to do any reactive power support. So the moment there is a fault detected, all these DGs disconnect from the grid and leave the grid, the other established generators in the grid, to handle these kind of fault conditions. Okay, so this makes it very difficult for the grids to operate. Okay, and all the DGs want to generate maximum output. So irrespective of the demand that is available in the grid, they would like to generate maximum and then pump it into the grid and maximize the revenue. So unless this situation changes and people are large renewable energy parks, unless they take up reactive power support and try to schedule their power output according to the demand in the demand of load in the grid, this is going to be a main issue in the operation of the grid. Okay, this is being addressed. I'm not saying that this is a scenario that is that will be available in the future. What I'm saying is, at present, when we have small generators connected to the grid, this is their objective, and this is what is going to be a problem. Okay, so now let's stop with the smart grids, and I think I have put the requirement for machine learning in its proper perspective. You have seen how the grid is very complex. It is spread over a wide area. It is having a spatio-temporal type of characteristic. It is spread over very large area, and it is having large variations in time. So the loads are getting connected, disconnected. There are seasonal variations. There are climatic variations. There are distributed generators, which are generation characteristics. Inherently variable generation is available. So you can see the complexity of the grid. And we have tried to emphasize that manual operation of these kind of grids is not possible. It is impossible, and we need to have software tools to help us operate and control these kind of grids. So what is now? Now it's time to come into machine learning. and take a look at what is machine learning and how do we incorporate this into the electric grid. Now, I understand most of the participants here are all basically, I think, from the computer science background. There may be a few electrical engineers. I'm hoping there are a few. So machine learning, I don't have to talk about machine learning actually to this audience. I'm sure you know what is machine learning. Okay, so machine learning is a subset of AI. There has been a continuous shift in terminology connected to artificial intelligence and big data and the subsets of this AI. So now machine learning is defined as a subset of AI, and it is basically relying on statistical models, okay, to enable machines to improve with the continuous learning experiences. So that is a very broad and all-encompassing definition of machine learning. Okay, so we'll see. I won't give too much importance to the definition. I would rather rely on the case studies that we take up to bring in this aspect and see in what ways it can be incorporated. Okay, so where is machine learning going to be used in power system? So you can see I've listed a few that came to my mind. There may be there may be many more, and there may be subsections of these applications, these areas. Okay, so one area where you can have machine learning is to help the operators, the load center operators in power system diagnostics, in control and operation. You can have diagnostics when there is a fault. You can simulate various scenario of fault conditions and prepare which breakers you should open and what kind of generators should be ramped up or ramped down, and all that scenarios of how to handle a fault and these kind of things. So power system diagnostics can be done before a fault is occurring and even during a fault, how to handle the fault, okay, depending on how the fault is developing. Whenever I have a major fault in a power system, the fault actually develops over a few cycles. Okay, and during the fault development, you can see, you can learn, you will get indicators about how to handle this fault in the most optimal manner with the minimum interruption in the services. Okay, so power system diagnostics, very important area where you can have machine learning. You can also definitely do it in operation and control. You can come to the distribution level and you can look at customer load profiling and distribution level utilities that are going to do distribution level operations in a grid. They can use machine learning for customer load profiling, and I will be talking about this in detail with the k-means clustering technique. Okay, and then you can have machine learning in a very big way in cyber security, because all this now the entire operation control, all this is going to shift into cyberspace, and they're all going into cloud kind of applications, and you will find that cyber security is going to be a very major requirement in a safe and reliable operation of the grid, smart grids. Okay, so cyber security, definitely you will require large doses of machine learning. Okay, so recent developments in monitoring systems and sensor networks dramatically increase the variety, volume, and velocity. So volume, variety, volume, and velocity, this is a very common phrase used in big data. So this should be, you will feel at home in these kind of statements. You can see that whenever I am going to automate a particular network, I am going to add IoTs or sensors, and you will have, if you take the case of an old grid, then you had in these substations, you would measure voltages and currents, and the RMS voltages and currents will be measured, and these would be sent to load centers, load control centers. Now we are going to have PMUs, phasor measurement units, which are going to sample the voltages and currents with much better frequency, sampling frequency. They're going to take 200, nearly 200 samples per second, and then that kind of a sampled value is going to be time stamped with a common GPS clock, and you will have the ability to look at the network in terms of synchro phases. Okay, you will have synchronously rotating phases of voltages and currents, and that kind of a view of a network makes the control and operation very, very efficient. Okay, but what is a price we pay for that? We have more volume of data. We have data with varied sampling rates. Not all the parameters need to be sampled at very high rates. So there are low sampled data, there are fast sampled data. There is a large increase in volume of the data. So you have all these requirements, all the ingredients which demand a big data implementation, and naturally bring in machine learning. Okay, so modern power systems, the focus is on rapidly modernizing monitoring systems, measurement, data availability, big data handling, machine learning approaches to process high dimensional heterogeneous spatiotemporal data. So this is the punchline. Okay, high dimensional heterogeneous and spatiotemporal data, the data that varies over space, of the terrain, of the geography, and it also varies over time. Okay, so that is in nutshell what is going to demand a big data and machine learning in grids, smart grids. So I would like to take a small breather. See, this has been a monologue. I've been just speaking for the last I think 1 hour. I think I have another. I think it goes till
1:30.
1:30. Okay, so it goes another hour. So I would like to take a small breather and take a feedback. Anybody has anything to say, because we're all academicians in this area. So I don't know whether I have put the things in proper perspective.
One request from the audience, sir, that please put on the camera.
Put on the camera.
Yeah.
Okay. Oh, definitely, I will do that. Yeah. So I think now it is on, but I have to stop presenting, isn't it? Or you can see me.
Yes, we can see.
Oh, okay. That is good. I was thinking of I was of the opinion that if I don't have my image, then this slides appear larger. Is it the case? No, that is okay. So anybody has anything to add to whatever I have said, or any comments to make? Professor Shashidharan, you can, if you want to add something.
What I understood is, far you were telling the basics of how, what, and all. Now learning. So
No, I had not come to machine learning, but because to motivate people to go into machine learning, motivate electrical engineers to go into machine learning, we have to put things in the proper perspective. Okay, to show where why machine learning is required, or is it that in academics, in many areas, we just talk about various techniques where even in places where they are not actually required. Okay, but what I wanted to emphasize was machine learning is very much required in electrical grids, and electrical grids is a big opportunity. When we go into the modern type of grids, it opens a very large opportunity for people who are skilled in these kind of techniques.
On other side, there are a lot of computer science students doing cyber security and machine learning and everything applied to smart grids.
Yes. So I think even they would have seen the potential for deploying all their skills. Okay, who are those who are skilled in cyber security? You are going to have lots of opportunities in securing the grid. Okay, so grid security is going to be a very major concern. So there is a lot of opportunity for cyber security people. There are a lot of opportunities for big data analysts, data mining, machine learning people. So that the whole gamut of artificial intelligence, whatever we have, is going to be a very big player, very big part of the modern grid. And that's what I said, the modern grid is going to have equal importance to be given to electrical engineers and computer science professionals. Okay, if I go out and say that computer science people are going to have more importance, I won't be lying. Okay, so the basic infrastructure is there. It has to be upgraded definitely. Communication infrastructure has to be added. A lot of communication is required in smart grids. Now, when that is done, then what will be required is these kind of machine learning techniques to be adopted and people to be upskilled, skilled in these kind of areas. Okay, so I think that was my intention in the first part. Now let me go to the next part. Okay, so anyone has to add, anyone would like to add something to this to make it a more lively session? I think most of them are academicians who are teaching, and what is their mix, Shashi?
Yeah, lot of people in teaching, somebody from industry.
Okay. So anyone wants to add something, this is the time. Then
we have people from which Mr. Amanji. We have people from Abu Dhabi.
Okay. Yeah, I think no one is coming forward. So I will continue. Okay. Yeah, I will continue. Okay, so I will go back to my presentation and let's see the further slides. Okay. So here on the screen you will find you have a simple diagram or a symbolic diagram showing what the grid of the future will look like. Okay. It's a very you can't actually put a smart grid in all aspects on a single diagram. Okay, so this is basically how the power flow in a smart grid will be. So you have the conventional generators, the thermal. You can see the chimneys of the thermal power plant here in the center, and then you have solar generation, you have hydro, you have windmills, all that in the generation part here. And these and there are some storage, battery storages, or flywheel storage, or pumped hydro kind of storages on the next layer. And then you have the consumers on the outer layer, basically the consumers in the outer layer. So you can find on the outer layer also there are windmills and solar power plants. These are the on the rooftop solar power plants, or very small micro scale of generation that you have in the customer premises. Okay, and you find an electric vehicle parked here, a diesel generator as a backup for a particular community here. So this symbolically represents what kind of a grid architecture, the power flow, what kind of an architecture you will have in a smart grid. Okay, so in what way is it different from the conventional grid? Okay, so you had all this thermal power plants, hydro power plants there. In addition, you have a large solar power plants and large wind farms in the center, and you never had to have much of a storage in the conventional grid, because these thermal and hydro power plants, thermal power plants particularly were very stable, and there was and they could handle the base loads very efficiently. Okay, so you didn't have you could have a spinning reserve in these scenarios and take the demand, the predicted load forecasted demand very easily with this kind of a setup. Now you are going to have storages incorporated. You are going to have small generating stations incorporated. You are going to have additional electric vehicles added to the grid, and whenever a vehicle is added with a 30 to 70 kilowatt hour batteries, then these form a very large component of the power demand. Okay, if you have large number of electric vehicles added and they have a particular charging pattern, they are all charging at night. For an instance, if I say all of them are going to charge at night, then they are going to impact the load demand in a very drastic fashion. So you have these kind of complexities creeping in with the kind of a smart grid. Okay, so let's go into machine learning and big data and look at what kind of data is actually available for analysis. Okay, so if I take the role of big data, you have field measurements. I talked about IoTs, an explosion of sensors and IoT in the modernized grid. So there will be a large volume of data coming in, heterogeneous data from the field measurement. You have weather satellites giving you weather data. Why this is important is I'm going to have renewable energy in a big way in the grid. So I need solar data, I need wind data, I need all kind of weather data to make forecast regarding the generation from these kind of generators. Okay, then I have geographic data. I need market data because I should know there are going to be power markets, just like stock market. There will be a power exchange market. So how is that data going to be? I require inputs from the power data, and then inside this, with all this data coming in, I have to do certain functions, and that is the asset management, distributed generation management, operations planning, and fault detection and protection. Okay, so these are the whatever is inside the circle are the main operating parts of the smart grid, and this will be supported by a multi-scale unified model. And we will see what kind of a model is this. Is it a data-driven model or a deterministic model? Okay, we already ruled out deterministic model just by looking at the sheer scale of sheer size and scale of the grid. So this is not going to be a deterministic model. It is going to be a data-driven model, a model derived from the data. Okay, so those are actually the key words in this slide. Okay, data-driven model, various functions that are required, and various data that is coming as an input. Okay. So this is another slide which is trying to bring in what kind of role a machine learning is going to bring into the smart grid. So I will skip this. I think there are a few things that I can skip. Okay, so this is one example of a DeepMind prediction in 2018. So this is a prediction for a load. Okay, this is a load forecast. 36-hour look ahead load forecast. So it was this was forecast 36 hours ahead using neural networks, and this is for planning the generation. Okay, this is for planning energy generation from a grid. So you can see the predicted is a blue curve and the actual is a green curve. So even with a very sophisticated prediction hardware and software running to predict just 36 hours ahead of you find that there is a wide variation in the pattern is more or less matching, but still you look at the absolute error in prediction, it is quite large. Okay, so the ramp down portion is almost correct, but the ramp up regions there is a large error. Okay, so those who are familiar with difficulties in ramp up and ramp down of conventional power generators, they will appreciate the fact that ramp down is predicted quite reasonably well, but the ramp up part is wide off the target. Okay, so this is just one example of what ML can do. Okay, and it's quite important part in the whole scenario. Okay, so these are the domains. Okay, so I think I will just skim through all these slides, and then I will go to the hands-on exercise that we have to do. Maybe I would like to do one exercise now, and then one in the afternoon session. Okay, so these are the domains. I think these slides will be provided, and you can take a look at these domains. So you have, if I spend a little, just a few seconds here. So these are the components: distributed energy resources, there is one component, distribution network, distribution and transmission network, grid operations, operators, forecasters, and market on the grid, and the customer network. So you can split it into three major parts. Okay, and on the bottom you will find a few terminologies used in smart grids. Okay, so one terminology here, prosumer. Okay, I'm trying to highlight it here. The prosumer is a producer and consumer. So basically, we expect to see more and more people having small solar power plants or wind generators in their premises. So they'll be not only consuming power from the grid, they'll be also producing power, and these kind of connections will be called prosumers. Okay, producers and consumers together. Okay, so that is regarding the areas in smart grid, and what are the applications of big data and machine learning in grids. So I have shown a few areas here. So anomaly detection, electricity theft, unauthorized solar interconnections, and those kind of things. Spatio-temporal forecasting, load forecasting, short-term, long-term forecasting, system monitoring, state estimation, and visualization of systems, very important in control and operations. Okay, distribution system controls, what kind of networks, deep reinforcement learning techniques and things like that. And equipment monitoring, how to do a monitoring machine, monitor a large generator and schedule maintenance, and monitor and predict a particular fault in the generator, and those kind of things. Those are also important parts in the important roles for machine learning in these kind of areas. Okay, and here you come to the customer behavior analysis, and that is what I talked about, load profiling of customers, and this we will take a look at this in the afternoon. Okay, so we'll do a small case study of this in the afternoon. I will show you MATLAB programs and K-means clustering in this. Okay, so this is what we'll be seeing. So what are the various techniques that are used in these kind of machine learning applications? So we find that these are the percentage of various techniques used. Time series is around 40%. So when you come to clustering and regression is the largest used technique, and clustering is very close. Then you have this random forest and decision trees and all very closely followed. So these are the common techniques that are used in machine learning, and we will. There is another slide here which shows what kind of a recent application has been done. Okay, 2019, 18, 16. So you can see what are the techniques used and what is the area in which it is used. So on the top you have load forecasting, and then you find the K nearest neighbor regression techniques used, random forest regression used, and you can see a few examples. This is not exhaustive. This is just I want to put a slide where you can take a look at what are the kind of techniques that are used and in what area in smart grid these are going to be used. Okay, I think this will be of interest to computer science professionals. They can see and what kind of a technique is used in which area of the smart grid. Okay, so what are the common machine learning techniques used? We know we can classify into supervised and unsupervised learning. So we'll be using K-means for our case study. That's why it's highlighted here. We'll be using clustering, and in clustering I'll be using K-means. Okay, so that is. And what is the actual challenge? So before I go into the hands-on, I would like to spend a few minutes in this slide, in this particular slide. So we have talked about not being able to analyze a very complex, very time-varying, spatially varying grid in a deterministic manner. Okay. So, so this kind of an equation where Sj here in this Sj, this equation here, Sj is apparent power, and if I try to calculate power flow in a grid, okay, in terms of deterministic equations, okay, in deterministic manner, if I try to do a power flow of a grid, including all the node voltages and node impedances, bus impedances and node voltages. Now, if I try to do that in a grid of the complexity that we have seen, we have actually seen a very granular grid. We can, if you zoom in deeper, the grid is much more complex. Okay, so that size of a grid, if I try to do a deterministic evaluation, then I know that it is going to be impossible for me to do. So then the only way I can handle this kind of a situation is try to create a model based on statistics and those kind of those type of analysis. Okay, so when I compute the statistics of electrical parameters and use that information to create a model based on the statistical and probabilistic distribution and statistics of power flows and voltage and current parameters and switch parameters, which load is connected, which load is not connected. So if I take and all these parameters, do a statistical analysis, and then try to develop a model, that is the model that I'm going to be able to use. Okay, so when I look at it, I am not going to have a model in which I am having a deterministic equation and then generate data. Okay, usually we are all used to having deterministic models which give us operational data. So whenever I'm trying to study a system, I create a deterministic model based on the physical parameters that I'm going to have in my model. In my system, I create a model and then generate data from that. Okay, so that is a usual flow of analysis, but I'm not going to have that. Here I am going to have to deal with inverse modeling problem, where I have the data from all my sensors available. I'm going to have a lot of IoTs distributed all over the grid, and they are going to feed me operational data. Okay, and I'm going to use that data, have an algorithm, either a stochastic or a probabilistic or statistical algorithm, and develop a model. And that is the model that I'm going to use for control and operation of my grid. So it is an inverse stochastic problem, and that is the kind of problem that I have to handle. Okay, so this I think cannot be emphasized more. It needs to be emphasized again and again to the academicians that this is the kind of modeling that is going to take place, and the usual kind of modeling that we are used to is going to be not implementable in complicated grids. Okay, so that is what I wanted to emphasize here. So I will skip this, and now let's try to do a hands-on with a simple machine learning problem. This will be a very simple problem, and I will in the afternoon I will take a slightly more complicated problem. But you have to understand that I am not going to talk about any deep learning or like Professor Raju did yesterday. So he talked about deep learning and scenarios of deep learning. That has to be built in stages, and in a session like this, we can only point you in that direction with simple examples. Okay, so I'm going to take a small industrial town. The scenario is mentioned here. So in a small industrial town, we have a smart meters in every consumer premise, and their recordings are located. Okay, so they are going to be having smart meters. Whenever I talk about smart grids, I am going to have smart meters in every consumer premise. And these meters are not read once in a month like we have the meter readings taken now. Those meters can be read many times in an hour. Okay, 15 minutes once, in 15 minutes once in 10 minutes. You can have readings from these meters, and every consumer meter can be read in intervals like that. Okay, so you have a so in a small scenario that we are showing here, we have a mix of DG, conventional electric grid with dominance of the grid. Population of a town is a mix of working people, retired people, commercial establishments, and medium and I think, yeah, one minute. I think I have misplaced that. Yeah, this is the example that we'll be dealing first. That is the example that we'll be dealing next. So the order is mixed up. I'm sorry. Okay. So this is the example that we will take a look now. So customer side, suppose I have suppose I take the customer in a smart grid. Okay. So what is the kind of a customer that I will have, and what are the type of issues that a customer in a smart grid will face? And then we will talk about how the energy bill optimization, this should be of interest to everybody. So how the electricity bill can be optimized for a customer in a smart grid. Okay, so we'll take a look at that, and this has implications in demand side management. So I will take a look at this first and then go to the more complicated example. Okay, so customer is having two type of loads. One is a fixed load and other is a shiftable load. Okay, so if I have lights in my house, fans in my house, they're all fixed loads. I cannot shift that load operation to some other time. If I am feeling a bit hot now, I would like to have my fan running now. If I need light in my room, I would like to switch on the light in my room right now. So I cannot shift that load. So there are some fixed loads in the customer and there are some loads like a washing machine or a pump for pumping water. So a washing machine can be that operation can be shifted to another time. So that can be done. So I have some shiftable loads, a pump which is used to fill water to my overhead tank, that can be shifted from the present time to some other time within a manageable time span. Okay, so shiftable, I have two kind of loads first of all. Then the shiftable loads have limited period in which they can be shifted, and the tariff is not a tariff that we are used to now. It is a time of the day tariff. So some parts of the day you have higher tariff rate, some parts of the day you have lower tariff rates. So that type of a tariff is called the time of the day TOD type of tariff. Okay, so that will be the kind of tariff you will see when smart grids are implemented. Okay, so what is my objective? Having said all this, the objective is to optimally shift the shiftable load and create a kind of a load profile which will give me minimum energy price. Okay, so I am going to look at from the side of a consumer how to utilize this kind of an optimization technique. If I am a consumer, if I want to reduce my electricity bill, how can I use a simple optimization technique to have the bill brought down to the minimum? Okay, so if I do that, I have a rider. What I mean by a rider is there will be a penalty. So if I stop here up to this stage, then you will find that if I do this, then most of the shiftable loads will be shifted to areas of the day where I have the least tariff. Okay, so we'll look at this in detail. But if I do that, there will be large spike in my demand in times when my tariff is the lowest. Okay, so that will not be acceptable to the distribution company, and they will penalize a customer if his maximum load to average load ratio is very high. So this is also to be kept in mind. Otherwise, if I allow the consumer to minimize his price, then he will end up giving headache to the distribution company by having large spikes of demand at times when the tariff is the lowest. Okay, so I think you have got a broad outline about what is our objective in this particular example. Okay, so this is what we have. I have taken one consumer. He is having a fixed load here. So I have marked the fixed load here. So 300, 200, these are all watts in various hours. Okay, so starting from 0 hour, going all the way to 23 hours, then you can find that there is a fixed load, that pattern that a particular consumer has. Now, if you ask me, is it going to be fixed in all the days? No, it is a typical day distribution. This is the kind of distribution you have on a typical day. Okay, and then that customer has 4 shiftable loads. Okay, so you have 4 loads having 1500, 1000 and 200 and 580 watts capacity. So you can look at one as a washing machine, the other as a pump or a heater, a water heater or some things like that. So you have 4 shiftable loads here. Okay, their start times are given here. So you can see that the load 1 starts at 6 o'clock, 6 hours. The load 2 starts at 16 hours and like that. So the starting times are shown here. And by how many hours can you shift it? That is also shown under the heading flexibility. Okay, so I have 4 shiftable loads. Their normal starting hours are given here, and by how many hours am I allowed to shift them, that is also given here. And on this side, on the duration, you can see that if I switch on that flexible load at one particular time, then I have to allow it to run for continuous 3 hours. If I talk about the case of the first load, then if I turn on the first load at some flexible time within that duration, then I have to allow it to run for 3 hours. Okay, so what is the duration required? That is also given there. So these kind of information is provided in an Excel sheet, and T of D, the rate at every hour is given here. So you can see in the night hours, 0 hours to 5 hours, 5 in the morning, you have a rate of 3 rupees per unit. 6 onwards, there is a rise in the rate, and then in the afternoon it is medium, it is quite low, and then again in the evening the price for energy is higher. Okay, so this is the kind of tariff that you are expected to see when a full implementation of a smart grid is done. Okay, so that is what you will see. And then now let me go to the Excel sheet. Before going, I have shown 2 curves here. One is the original load curve. This includes the customer's fixed load as well as his shiftable load. In this original load curve, the shiftable load is started at the original starting time, okay, without any optimization. So if you take a look at the start time, then I have indicated some start times here. So these are the times at which these loads will start if there is no optimization. If I don't have any optimization done, then these loads will start at these times. Okay, so this original load curve has the fixed load as well as the flexible load starting at the original start times without any optimization. Okay, and this is the time of the day pricing. So you can see till 5 o'clock the price is around 3 rupees, then it goes up, and then in the afternoon again it is a bit low, but it never comes down to 3 rupees, it stays a bit higher, and then in the evening again it goes to a higher rate. Okay, so time of the day pricing and the original load curve is shown there. And on the next slide, you will find the original load curve compared with the optimized load curve. Okay, so as expected, see, whenever I try to reduce the price, the only logical way to do it is to push the shiftable loads to the areas where the energy rates are lower. Okay, so you will find this is the original curve without optimization, and this is the optimized load curve. The area under these curves will be the same, that is the units consumed by the consumer remains the same, but some shiftable loads are shifted to reduce the price. So you will find a bulk of the loads are shifted to the morning hours, because the morning hours we have seen the lowest tariff, and some other loads are shifted to the afternoon hours. Again, in the afternoon the tariffs are lower. So like this, the loads are getting rearranged when I optimize the load curve for lower prices. Okay, so with this, let me go to the Excel sheet and let me show you actually how this problem is formulated and how it is implemented with a built-in solver. Okay, so let me go to that. Let me shift to the Excel. So I'm sure most of you, all of us have used Excel, and maybe we have also used the solver in Excel. Okay, 1 minute. Yeah. Yeah. Is it visible? You able to see this?
Yeah, it's coming up.
Oh, okay, okay. So this is that example. So I have shown parts of this in the slides that we have seen. So you can see the fixed load here, the time here, and the time of the day rates here, and you can find the flexible loads shown here, the duration, the flexibility, the start times, and the power ratings. Okay. So with these all these things given, I'm going to optimize the energy. I'm going to optimize this distribution of loads to get the minimum energy, minimum price, not minimum energy, minimum price. Sorry, okay, minimum price. And this is my objective function. So if you look at this, this is my objective function minimization that I'm going to do. This is the objective function. Okay. Now, if you look at this, it can be a bit confusing, because what I'm trying to do, I will come to the lower part of this sheet, and you can see, if you look at this part, if you are watching, if anybody is watching in their mobile, then this, I think it will be difficult to read it, but anybody, I think on a laptop, it should be readable with some difficulty. Shashi, is it?
Yeah, we can manage, but the font size is very less.
Yeah, very small. That is because I try to increase it, but then the graphs go out of the screen. Okay, so I think we'll manage with this, but I'll try to convey the idea, and then maybe I will send you the Excel sheet so that you can open it and take a look at it in your own leisure time. Okay, so here we have the fixed load, and these are the flexible loads. Okay, 1500 rated flexible load. Okay, so what I'm trying to do is, I'm trying to find a place in this in this day where I can fit this flexible load. So all these flexible loads I'm going to arrange at particular time durations where the result will be my minimum price. So that is my objective function. So that is what is written here. Okay. So in Excel, I have written an objective function. I have used an offset command to take up this kind of a formulation of an objective function. Okay, so I'm up to this. If I try to highlight up to K28, up to this, the objective function tries to place all the loads on various time slots. Okay, how to find the most optimal time slot, that is what is written there. And then if I have the ratio of maximum to average beyond a particular value, beyond 1.5, then I am going to introduce a penalty function to make sure that the customers don't create very large spikes or very large peaks in their load consumption. So that feature is going to be written in this if command. Okay, I have an if statement here. That if statement relates to the penalty factor. Okay, so and this K28 that I've added is I'm adding the fixed load price along with this shiftable load price. So the first part is a shiftable load objective function where I'm going to vary everything. Then I have a fixed part of that is a fixed load whose price is fixed, and then I'm going to have a penalty factor added to penalize people who shift everything into one time slot and create a large demand peak. Okay, so this is what I have done. I don't know whether I will try to show you the solver and maybe explain a little about what is being done in the solver. Okay, so I will, when you go to data, you should have a solver here. It is usually data tools. Those things are all okay. Yeah, this is a solver here. I don't know whether I can increase the size of this. 1 minute. No, I think I can't increase the font or the size of the solver. I will try to put it in the middle of the screen. And you have to, if you, are you able to make out anything from this?
It's okay. It's okay.
Yeah, it's okay. So you have to put an objective, you have to select a cell and tell the solver which is the objective function, which cell is the objective function cell. Okay, so that we have to put, and then you have to put various constraints. Okay, so in my formulation, I have taken 4 cells and I have used them as my constraints. Okay, so that is what you have to do in the next 1 minute. Yeah, so I have added some constraints here. So you can see the constraints that are given here. So these are 2 constraints for each variable. Okay, one less than or equal to, one greater than or equal to constraint added to each variable. Okay, so like that there are 4 variables here for 4 shiftable loads, and then after giving the constraints, and how are the constraints coming? The constraint is coming because the load 1, that if I take this 1500 as my load 1, then it has to conventionally start at 6, and it can be flexible by plus minus 4 hours. Okay, so either I can start it at 2 o'clock in the night, or I can take it and start it at 10 o'clock in the morning. So that is the range within which I can switch on load 1. Okay, if I take the load 2, then it is supposed to start at 16 hours. It can go plus minus 7 hours. Okay, so that is what is given in the constraint. So how much I can shift each load, so that upper and lower boundaries are given as a form of constraints here. Okay, and in the lower part, I am selecting a GA-based, genetic algorithm-based solver for running this. Okay, and that is what you have to do in this. And the minimization, I have clicked the minimization here because I want to minimize the objective function. So objective function is minimization, and I want to have the minimum price coming after the optimization. So this is what I was trying to do. I think okay. So if after I run this, you will 1 minute. Excuse me, 1 minute. Yeah. So after I run this, this is my objective function. So suppose I start with my start times. Okay, I start this before optimization. This is already run. So before optimization, suppose I had my conventional start times here. Okay, I start with these values. Okay, and I think there is something I messed up the. Okay, I think I unintentionally I changed something in my. Yeah, now it is okay. Okay, now after doing all this, if I run this, so what does it look like? Okay, let's take a look at this. And now what I have done is I have changed these variables to my initial values. So I start from the start time itself, and then I try to see how these loads are shifted to give me a lower energy price. Okay, so the energy price now is 204, and the fixed energy price is 72, and the variable energy price is 56. So what I see is if I add 72 plus 56, then I come to somewhere around 130, and then I have a penalty factor that is there because the spike, the load that I am having is having a peak versus average ratio which is more than 1.5. Okay, so that is the reason why there is a penalty there. So if I add all the 3, the fixed load, the variable load, and the penalty, I come to a daily price of 204. Okay, now if I solve it, if I run this solver, let's see what happens now. Okay, So it has already found the solution, and now you find that the total price has gone down to 172. The fixed load obviously remains at 72, but the variable load pricing has come to 33, and obviously the penalty also would have come down. Let's look at what is the peak to average, the maximum to average ratio. Previously it was around 2.7, and now it has come down to 2.23. Okay, so now you can find that this optimized load curve has shifted the shiftable loads to 2 hours. Now you found that I started this with the value of 6. Now the optimal value of this is when I have this load starting at night 2 o'clock. Okay, so this started at 16. Now the optimal value is at 18 hours. This started at the value of 10, and the optimal value is 13 hours. And this started with a value of 12, and the optimum value is 13 hours. So now you find that after running it, all these loads have been shifted to their most optimal value within the constraints, and also taking care of the penalty function, which avoids a use of high load demand peaks. Okay, so this is what the first example shows. I don't know whether this is clear, this example is clear. So you can take a look at the original load curve here, the time of the day pricing here, and the optimized load curve here. And you can see very clearly that some part of the original load curve has been shifted to the low time of the day pricing areas, and then the optimal load curve is generated, and which also takes care that you don't get penalized too much for creating very large load peaks. I'm sure the electrical engineers will be able to relate well with this kind of an example. I don't know whether similar kind of examples are there in communication networks. Maybe there are similar kind of scenarios in communication networks also, and maybe the other people also can relate to this kind of an example. So any questions on this, please? Anything to add in this particular example?
Participant side?
Yeah.
Any concerns? Is it okay?
I don't know. I'm a bit worried that no one is speaking.
Participants, please interact.
Yeah. So we are all academicians. It would be very bad. I'm sure all of you agree. If your students didn't say anything in the class, you would be very much upset. It has been a monologue. Now I have been talking monologue for a very long time. So everyone is typing yes, it is okay. I don't know how to interpret it, whether it is really an okay or they are all feeling hungry.
It's clear.
Maybe many of them are hungry. It's 1:30. So I don't know. I think it is a fairly simple example, but please don't go by its simplicity. This can be scaled up. Better techniques can be done in optimization. Better techniques can be brought into the optimization. I have made it in Excel because Excel is something that is available to everybody. All of us have Excel in our laptops, so you can take this sheet and run it. I have a MATLAB program written for this. Okay, if you want more complicated programming, you can go to the MATLAB. But this example, even though it looks very simple, is a very real example. It can be made more complicated, more constraints can be added, and it can be extended in its role. Okay, so demand side management emphasizes on the customer side. Okay, and the customers also would like to have some benefit by paying lower prices when you have a TOD type of energy metering available. Okay, so when smart meters are introduced, TOD pricing is introduced. then you would also like to have this kind of an optimization. And I think in the afternoon we will take a look at load profile clustering, load profiling using clustering techniques. That will be a little more complicated, but nowhere near the deep learning complications. Okay. So I think, yeah. Wow,
Just wait.
yeah, somebody said something.
Valentine, just wait.
Yes, sir. Sorry, sir.
Yeah, no problem, no problem. Yeah, I can understand the hurry. Okay. Yeah. So if nobody anyone has anything to add, any feedback will be welcome. You can turn on the video and we can see. I can also see a few of the participants. Okay, you asked me to turn on my video. So if a few of you turn on your videos and share your experiences, if you are teaching machine learning and if you are teaching smart grids in your institutions, if you have something to add in this area, I would also be very interested in listening to that. There is only one participant who is.
Dr. Nambiar sir is there from Amrita University. Sindhu Tambati is there from Amrita University.
Are they there?
Yeah, they are all here.
Oh,
Yes,
okay,
yes,
okay.
Venu. We are here.
We are here
here.
and you're not
Yeah, yes.
saying anything.
Yeah, it's
Okay.
nice.
Nambiar
Because
sir is
nowadays
there.
most of us
Nambiar
are
sir is
working in
also
the
here. Nambiar sir is also here from Amrita University.
I don't know in what name is he. He is there in his own name or?
Nambiar
Professor
sir.
Venu.
He is there.
Yeah,
he is there.
Venu.
Yeah.
Yeah, my camera is not working.
Okay, sir. Okay,
Anyway,
sir.
I am listening to you very carefully. It was a new experience for me, the time of the day metering and how you are going to flatten the load curve.
I can't believe that, sir.
Excel sheet I could not see because I am using my mobile phone.
Yeah, okay.
Anyway,
Okay, sir.
congratulations
Thank
to you for your nice presentation.
I'm very happy to hear your voice, sir.
But I joined late only because I just saw message and the link only by 12:30.
Okay,
I was outside.
Sir,
Anyway,
evening also we have session, sir.
Now?
Evening also we have session at 3 o'clock.
Yeah. I'll talk something about.
What time you will start?
Sir, I'll start at 3 o'clock.
About 3 o'clock.
3 o'clock.
3 o'clock. 3 o'clock.
Is it continuation of this?
No,
It will be
in
continuation of this?
Yeah, it will be a continuation of this in the sense that I will talk about k-means clustering for customer load profiling.
Okay.
Yeah, I will write the program. I will show you the program. I will do everything by in steps.
Actually, we all joined late only, because we got the link and also we circulated to our PhD scholars. So many of them working in the same area.
Okay.
Yeah.
But I don't know whether they have very big expectations, whether I will fall very short of that.
It was really nice. It was really nice. Hands-on also, it's nice.
Yeah. So I will send you this sheet, even though it's a very simple sheet. It can form a template for bigger, more sophisticated analysis. Yeah. So I think you can give it to your students as an assignment. And,
actually, even RET students also, they're working in that distributed generation side and all that cost minimization and all, they're working in that. So I think it will be useful. We send the link to all of them because today they're having classes also. So I
yes, definitely. So I think Shashi, we can give them. We can stop and maybe let them go and have their lunch.
Yeah, we shall stop now and we shall continue at 3 o'clock.
Okay. Thank you everybody for a very patient hearing. I am sure it must have been very difficult. Okay. I will try to. Yeah. Okay. Thank you.
Thank you, sir. We will have a short lunch break between 1:30 to 3. We will meet again at 3, where sir will continue more on the topic Smart Grid in ML. See you again at 3. Please join 5 minutes prior to the time. Thank you, everyone. You may please leave now. Thank you.
Thank you.
So can we continue the session?
Yeah, we shall start. We shall start.
ശശി
Yeah, Madam sir, തുടങ്ങല്ലേ?
തുടങ്ങട്ടെ.
Campaigning team, please announce.
Sir?
Sir, we can start.
Okay, sir. Good evening, everyone. Welcome back. During the last session, we had Professor Venugopalan Kurupat, sir, who shared his knowledge on the topic Smart Grid in Machine Learning. Now, he will continue from where he had left the last session. Over to you, sir.
Thank you, Sharath. So we will, I got a few mails from the previous session. It seems the Excel sheet exercise that we did, there is a little clarity to be brought. So I'll quickly go and spend 5 minutes on that previous hands-on exercise, and then carry on with the K-means clustering. Okay, so it seems when I presented the objective function with the Excel solver, there were a few things that people were not very clear. So I'll just go and finish that and try to bring some more clarity into that, and then come back and start with the clustering exercise. Okay. So 1 minute. Just let me present. Okay, so this was the exercise that we were seeing. So I will not repeat most of the things. I will just concentrate on how the variables were given for the solver, how the variables were specified, and how the objective function was given. Okay, so this Excel sheet I will send you along with the materials for the FDP. You will get this Excel sheet. If you still have doubts, you can take a look. Okay, so let me again show these are the 4 variables. See, we have 4 loads that need to be shifted. Okay, so one load having 1500 watts, supposed to start at 6th hour, hour 6 in the morning, and it can flexibly take plus minus 4 hours. Okay, so like this we have 4 loads. So the duration of the loads, duration in hours for the load to run, all that is given. So this data is given, and this is what is going to be optimized. Okay, so I'm going to flexibly place these 4 loads such that you get the minimum energy price. Okay, so that is my objective function. So when I showed you this objective function, that is what is written there. Okay, there is only one command called offset, which is for selecting the rate from the TOD, time of the day rate, how to fix, how to select a particular rate for a placement of that load. So that is the only statement that needs to be seen. So offset is one command that maybe you will have to try once or twice in Excel, and then if you understand that, you can very easily make out what is written in the objective function. Okay, so objective function is given, and these 4 variables that I am going to get, these are the starting hours for these 4 loads. Okay, suppose the load starts at 4. The first load is starting at 4. Okay, then you can roll down here to this first load and see that it is starting at 4th hour, and it will continue for 3 hours because its duration is 3 hours. Okay, similarly the second load is starting at 13 hours. You can see it is 13 here. So it is starting at 13 hours and its duration is 2 hours. Okay, the third load is also starting at 13 hours and its duration is 5 hours. Okay, and the fourth load is starting at 12 hours and its duration is 1 hour. So that is what is happening here. So these are the 4 variables that are going to be utilized for placing the loads. And after placing the loads, the objective function will calculate, depending on the rate at that particular hour, what is the price to be calculated. So that is what is calculated and shown here. This value 167 is a sum of 72.9 plus the price of the fixed, this is the price of the fixed load. 28.02 is the price of the variable loads, all the four variable loads put together, and 66.95 is the penalty factor. So all these three yellow values put together is my objective function value. Okay, so that is what is done there. I will run it. They wanted this to be run again, possibly wanting to see how much time it takes, or I don't know what. So I will run it again. 6, 16, 10, and 12 are the starting times given here, 6, 16, 10, and 12. So I take my initial value to be the non-optimal load values. Okay, I'm assuming that it is starting at whatever start time is given. Okay, and now after running, you will find that these starting times are varied. Okay, after optimizing, you will find these starting times will vary. These are the four variables that will that will reflect the optimization process. Okay, so here you can see the original load curve, the time of the day pricing, and the optimized load curve. Now it is the original and the optimal is the same because optimization has not been done. Okay, so that is what these two load curves indicate. Now there is it is before optimization, so the original and the optimized load curves are the same. Okay, so now if I run this, you will find that these values, now it is showing 56.42 as the flexible load price. Okay, now this is what will go down, and along with this, the penalty factor also will go down. Okay, because the peak to average now is 2.4, 2.5, and if it goes down, then this penalty factor will also reduce, and as a result, the sum of all the three will also come down. Okay, so that is what was happening in the optimization. Now I'm going to run it, and now you will find when it is running, I'm using a genetic algorithm based evolutionary solver. There are 2-3 options available. There is a simplex linear programming solver and a GRG nonlinear solver. So you can select any of that and then try this. If you change the solvers, or if you run the same solver 2-3 times, you may not come to the exact solution, because it may not always come to the exact solution. Okay, this is a genetic algorithm based solver. You can set the mutation rates and other things in the options, and then you can run it. Okay, so now I will show the running of this. So now it is running. It will take some time to run. Then you can see the change in this curve, the optimized load curve. Now that load will shift to a region where the price of the energy is lower. Okay, so we'll wait for it to finish, and then you can see the results. So it does take a little time. I think it should be done in a few seconds more. It will finish. So it has come to a solution, and now you can see this is the optimized load curve. So now there is a difference between the original load curve and the optimized load curve. The loads have shifted, whichever is possible to shift, they have shifted to a region where the price of the energy is lower. So TOD pricing is lower in this region, and it has shifted to that region. So this is what is a result that I have shown. And now you can find from 220 it has come to 167, where this value and this value is reduced. The penalty is reduced, and the flexible load energy is reduced. The fixed load cost of course remains unchanged, because it is not, there is no shifting on that. Okay, so this was what was the result that we saw, and I tried to explain the formulation, but maybe some things are still not clear. But those things can be very easily done if you refer to some manual. So and it's quite easy. I mean, it's very easy to do it. Maybe when you look at this file, it will be clear. So I think I can proceed from this. I will go to the next topic. Shashi?
Yeah, please.
Okay. Yeah. So I will go to the next topic. If there are some doubts remaining, maybe we'll take a look at it in the end. Okay. So I will take the next topic about load profile, customer load profiling using k-means clustering techniques. Okay. So let me go to that, and let me stop presenting the Excel and go and present the PPT. 1 minute. Okay. Okay. So let us go to the next topic. That is how to do load profiling of customers with k-means clustering technique. Okay, k-means is a clustering technique. So let us first understand what is k-means clustering. Okay, with a brief, with a very small example. Then I will show you a MATLAB file to make this more clear. I'll run a MATLAB file, and then 1 minute. Yeah. No. Chavi Okay, I'm sorry. So we can take a look at this. So now you find that it is a two-dimensional data having 1, 2, 3, 4, 5, 6, 7, 8. 8 data points are there. So it's a two-dimensional data given, and what is done is this data is plotted on a two-dimensional figure, two-dimensional area, and arbitrarily, randomly, two centroids are selected. Okay, so these red dots are the two starting centroid values, which is chosen randomly. Okay, and after selecting these two centroids, I'm going to measure the distance, the Euclidean distance between these data points to these centroids, and I'm going to categorize them into one group or the other, because now I'm having only two centroids. So obviously I'm trying to split these data points into two clusters. Okay, so how that is done is after selecting the centroid, I'm going to measure the Euclidean distance of point 1 with this centroid and point 1 with the other centroid. If this distance is smaller, then I will say that this point belongs to this cluster, belonging to this centroid. So I will color it here. I will color it blue, and in the other cluster, I will color them black. Okay, so like this, I take every point and I find the Euclidean distance between the two centroids and mark the point to be belonging to the nearest centroid. Okay, so this is how I start the k-means clustering. I hope that is clear. Now you find 1, 2, 3, 4, 5, and 6. 6 points are blue, and there are 4 points which are black. So this is done by measuring the Euclidean distance. So after doing this, after selecting the first the centroids randomly and doing this, then what is done is we find with these points divided into two clusters, we calculate a centroid. Okay, so the centroid is calculated, in a manner similar to we are used to finding center of gravity. Okay, so I find the centroid of these 6 points and then mark it as a new centroid. Okay, so these 6 points are used to find a centroid, and these 4 points are used to find another centroid. Okay, I will come to the mathematical equations and the things in the later stages. So after finding a new centroid, again I repeat this process. The first step, I calculate the distance of each point to one centroid and these two centroids, and decide whether it belongs to one cluster or the other. Okay, so I will again take the first point, see this distance, and then the first point and the distance to the second centroid, see whichever is smaller, and then that point belongs to that cluster. So like this, I again find a new cluster. Okay, I find a new cluster, and now I find the new cluster is like this. This point blue, this point which is lying at the bottom, now it has shifted to the other cluster. Okay, and one point which is very close to this centroid is shifted to this cluster. Okay, so there is a reorientation, there is a switching of points between one cluster and the next cluster. And again, with the new clusters given, I will again calculate the centroids and again repeat this. So these steps get continuously repeated until I reach a step where there is no switching of any point from one cluster to the other. So if there is no point switching, changing clusters, then it is at that point I stop this clustering. So that is the basic clustering technique, k-means clustering technique. For a small two-dimensional example with a very few points, I hope that part is clear. That is that clear to everybody? I think that is a very fundamental topic, and most of them are computer science, so we can safely assume it is clear, and then I will proceed. Okay.
Okay, fine.
Yeah. Okay. So now going from here, let me show some graphics, some interesting graphics. So you can see that there is some scatter plot. There is a lot of data plotted, and it's all in the same color. So it has not been obviously separated into clusters. Okay, so you can see from the very way the data is lying, 1, 2, 3, 4, 5. There are 4 or 5 distinctive clusters. This, and this are definitely distinctive 3 clusters. Maybe these 2 close together data points can be either considered as 2 different clusters or as a single cluster. Okay, so we can see that the data belongs to 4 or 5 naturally occurring clusters. Okay, so now if I do this k-means clustering, we will take that k equal to 5 and start this clustering. So what is the first thing that we do? We randomly select 5 points, okay, as the centroids, and then proceed with the process. Okay, so 1, 2, 3, 4, 5. 5 randomly selected points are taken as 5 centroids. Okay, randomly Gus cluster center locations. Okay, and then what is done is each data point it will calculate which is its nearest centroid. Okay, and then it will be shifted. It will be demarked into 5 clusters. So you can find the areas demarking the clusters. So all the points lying here belong to this centroid. All the points lying in this side belong to this centroid. All the points lying here belong to this centroid. Like this, I am going to demarcate. Okay, find which center owns which set of data points. Okay, so now after doing that, I find within that cluster, I try to calculate from my random selection. Now I come to a calculated centroid. Okay, so you will find the centroids shifting. The randomly selected centroid is now shifting to a calculated centroid. Okay, so after that, if I continue this process, then you can find in an animation, you can find the centroids moving with each iteration, and then this is the final centroid. So this is the final cluster that we get. So we get one cluster here, one cluster here, third here, fourth here, and fifth here. Just like we could see in the initial graph itself, we could have seen that in this graph or in this graph, we could have seen that there are 5 distinct clusters, and the centroids of these clusters should be somewhere in the middle of these clusters. So that is what we would expect to happen after we run it and come to the end of this cluster. So you can see at the end, all these centroids are at the centers of these naturally occurring clusters. So this is what we do in k-means clustering, and this is what we are trying to use. This simple technique, simple iterative technique, is what we are trying to use for load profiling. Okay, so we have a very simple technique, and many people feel that for time series clustering or handling quantities which vary over time, a load curve is something that if I measure every hour, then it will have 24 values. So it is a value varying with time. Okay, so very often people feel that signals and values, time varying values, cannot be clustered with simple techniques like k-means clustering. Okay, so we'll see whether we can do that and do get some meaningful output after doing this. Okay, so this is the fundamental of what we are trying to do. It is as simple as this. We'll write some MATLAB programs. K-means is a built-in command in MATLAB, so it is far more easier to do it in MATLAB, where you have a simple command to do it. And if you understood this, then the remaining part should be very, very easy. Okay. So before going into the actual program, now let us try to answer a few questions. So what is k-means trying to optimize? Okay, there are some questions that we always ask when we use iterative techniques. What is it that it is trying to optimize? Are you sure it will terminate? Will there be a termination condition, or will there be conditions where there will be situations where it will not terminate? Are we sure it will find an optimal clustering? How should we start it? How should we automatically choose the number of centers? Can we automatically choose the number of cluster centers? The number of clusters that we have, can we automatically choose it? Okay, so these are the questions that we should look into before we try to use k-means for any application. Okay, and there is something called the fuzzy c-means clustering technique. The only difference between k-means and c-means is in this each point belongs definitely to one cluster. In fuzzy c-means, each point belongs to one cluster with a membership function, with a membership value. Okay, so one point will belong 0.7 value to one cluster, 0.2 value to another cluster, and 0.1 membership value to the third cluster. So like this, it will partially belong to different clusters with varying degrees of membership. Okay, so it has its own, fuzzy c-means has its own advantages, but for our application, a simple k-means do the job. Okay, so these are some of the things that you should answer. I will not bother to answer this because this is predominantly a computer science audience. Okay, if had it been fully electrical people, I would have bother to spend some more time in this. But I think for this audience, it will be a waste of time. Okay, so how do we, only answering the last point, how could we automatically choose the number of centers to be in a cluster, or number of clusters that are available in the data set? For that alone, I think I should go into this slide. So if you are finding the number of clusters and the objective function value or distortion value, then you will find that there is a knee point, an elbow point here, not the knee point, the elbow point. And at that elbow point, whatever number of clusters you get, that is the most optimal number of clusters. So this is available in most fundamental theory. Okay, so we can automatically find it. If you look at a data set, and if you can see a natural clustering available, then possibly you can take it as a natural number of clusters. If you don't see any natural clustering available, then you can utilize this to find the optimal number of clusters. Okay, so that is what we do. Okay. So there is a MATLAB program in this slide, which is to give a demo about K-means clustering. I don't know whether this is a very simple program with a two-dimensional data given, and then you can run it and see how the clustering. There is a pause command there, so at every step you can stop it, and then you can see how the points are getting shifted. I will show this after when we go to the MATLAB. I will quickly try to run this. Okay, so what does the customer load profiling with K-means do? What is the motivation of doing it, and what are the factors that you should take into account when you do this? Okay, so the motivation for doing K-means clustering is it allows the distribution company to plan in short term and long term. Okay, so whenever I am having a distribution utility which is supplying to a community, okay, we will see a small community with different kinds of consumers, and when you have these kind of distribution companies, they would like to plan short-term and long-term load forecasting, and plan their resources, and plan how much energy they are going to buy from the market, and all those criteria. They would like to do some planning in short-term and long-term. So this profiling will help with that planning. Okay, it also helps the utility to identify the type of customers and their energy consumption pattern. Now, if I can do this, I can really learn a lot about the customer requirements, and also learn a lot of information, get a lot of information, which will help me provide better services to the customers. Okay, suppose I find in an area most of my customers have very low load requirement during the afternoon hours, then I can schedule a maintenance in that hour. Okay, so I'm just giving you some examples where the customer satisfaction and the customer service quality can be improved if I can learn about the customer load patterns. Okay, the consumption pattern. Okay, it helps the utility to formulate proper time of the day rates. Okay, if I am trying to maximize the rate, maximize my revenue as a utility, I would like to charge the customers when they are using the energy the most. Okay, and then the customer will definitely try to optimize it by shifting his load. So this goes in a cycle. So the last example, we saw an example from the viewpoint of a consumer. Now we are trying to take a look at what is the viewpoint of a utility. Okay, so this is if I can profile a customer, it can help me to create a proper time of the day rates, which will maximize my revenue. Okay, and it helps to plan the equipment upgrades and maintenance. Last time, in the last example, we saw one penalty factor which penalizes customers if their maximum load to the average load ratio is higher. Now, why were we doing that? We were doing that because if the consumers start demanding a lot of peak load and their average load is very low, then what happens is all the equipments that I am having to put as a utility, now I'm looking at it as a utility. So I have to put all my transformers, all the other equipments rated for the peak load. I cannot put these equipments for the average load and allow them to get overloaded during the peak hours. Okay, so I have to always put my equipment able to handle, that will be able to handle the peak load, and that I would like to keep that ratio, peak to average ratio, within the allowed limits. Okay, so this profiling will help me to plan for equipment upgrades and when to go for maintenance and things like that. It helps in estimation of storage and distributed energy resource provisions. Okay, if I'm having a lot of distributed energy resources connected with my community within my distribution area, then it will help me to schedule these resources and also plan for battery storage and other kinds of storage to improve the power quality. Okay, so these are the motivations for doing what we are going to do. This is the motivation. Okay, there are a few more, but these are the main motivators. Okay. So let's have a flashback. In our previous slides, I talked repeatedly about how a non-deterministic approach is the key to handling very complicated grids. Okay, so we at that time we emphasized that this kind of a deterministic equation will not be used. Cannot be used. And I have to always start from the data given by various sensors and IoTs and PMUs and other things. And this data is what I will process through an algorithm and then come out with a model. Okay, so the other way, having a deterministic model and then generating data and then trying to analyze it is no longer a viable alternative. So we have to go in the inverse stochastic problem. Okay, so when I start with the inverse stochastic problem, we'll see what are the implications of that in our application. Okay, so please keep this in mind, that this is the very important starting factor. So that's why I wanted to remind you about this slide. Okay, so let us look at, so I have taken a community having a few houses, something like 200 houses, 50 commercial establishments, 4 or 5 industries, and some random loads which don't come under any of these categories. Okay, so I'm trying to take a small community of consumers, and that community has a mix of all kind of consumers. Okay, so let me show you that mix. Yeah. So this is the mix that we were trying to see in our scenario now. We have a population, population of the town is a mix of working people, retired people, commercial establishments, small and medium industry units. Okay, so each of this is working people and retired people. They are households, but they have different kind of load profiles. Okay, so we have a healthy mix of all these people. And this mix is what is shown here. Okay, so the load profile that I'm showing here is the load profile. All these consumers have their smart meters, and we saw that the smart meters can read once in 15 minutes or once in 30 minutes. And what I have taken is data once in an hour. Okay, so if you to look at this axis, it will go from 1 hour to 24 hours. So this is the hour axis. This axis is the hour axis, and these are the different consumers. Okay, so there are 1,400, nearly 1,400 consumers available, and this is a plot of all the load curves. Okay, so it is coming as a surface plot, but it is actually basically plot of all the load curves of all different consumers. There is no particular order here. It is all mixed up according to the smart meter readings that I get from consumer numbers. Okay, so if I have to look at this data, okay, and try to find profiles of individual consumers. Okay, so this is what I am trying to do. Now I look at this data, this surface, and I have what I'm trying to achieve is to look at this set of data, 1400 consumer load data, and then trying to find out whether I can classify them, whether I can cluster these individual consumers into 5 or 4 different clusters. Okay, if I can do that, then what I achieve by doing that is I can get a representative load profile for each cluster. Okay, so I have all the load data here. They don't look to be having any particular shape which I can see. There is no pattern that I can visibly see. But what I'm trying to do from this is I'm trying to find 4 or 5 representative load profiles from this, such that I can classify these consumers into 4 or 5 different categories, and then I can find a representative profile from them, and then use it to meet all my motivation here, to meet all these requirements. Okay, so that is what I am trying to do. So these are the results. Okay, so now just to show you, I think we will come back to the result. Now I will switch to the rest of the analysis is in MATLAB. So I will go to MATLAB. I will open MATLAB, but this is what we will see in the end. Okay, so let me go to the MATLAB and start MATLAB. Okay. Okay. So let me adjust the windows. So I will try to spend some time on this program. So if you have anything that you can't understand, please interrupt me. Okay. I think first I'll clear everything. So clear all, close all, and CLC, clear the command window. So we have one program here. Before that, there is a k-means clustering program that I promised I will show you. So I'll just run that. 1 or 2 minutes I'll spend on that. So here, what we can see is we have a data which is a 2-dimensional data. Okay, you have 2-dimensional data, and it is we are taking that it has 2 clusters. Okay, so I'm taking the number of centroids equal to 2. I've commented wherever it is required. So number of centroids is taken to be 2. Okay, if you don't know this, then you can use the other technique for finding the optimal number of centroids. So this is a simple illustration. So I have taken it to be 2, and if I run it, this is what you find. Okay, so all these data points, after all the iterations are run, they come out like this. So you have these, all these data points are there. These are the data points belonging to this centroid. Let me make it larger. So this is the end result. I don't know whether the light greens are visible, but there are some points near this centroid, and there are some points near this centroid. Okay, so the data points and the centroids that are formed are visibly, they are in 2 clusters. So you can see that the clustering has been done. Okay, so you can run that program. When you get time, you can run that program, and you can pause it in between and see how it works. Okay. So I think there is a pause here. I don't know whether I can run it. So okay, so this is these are the two random centroids taken, and this is the first point that is coming into consideration. And if I enter and look at it, now there are some more points coming, and these 2 points belong to this centroid, and these 2 points belong to this centroid. Now you can find that in the first iteration, even though this point is closer to this centroid, okay, it is much closer to this centroid. It is in the first iteration, it is not clustering properly. Okay, the clusters are not formed optimally. Okay, so that you can see, and after the iterations are run, you will find that these points will shift automatically, and then you can see that the clusters and the centroids will be automatically coming properly. Okay, so in this stage, in the intermediate stage, you can see that there is a blue dot here. So this is very close to this centroid, but it is not properly clustered. Okay, so it is that intermediate stages that I'm showing. So after the intermediate stages, if you continue, you will find the centroid also moving into the correct position, and the points also getting shifted into proper clusters. Okay, so if you run it now at this stage, I think you can find that the clustering has been done. Okay, all these points are with this centroid, and all these points are with this centroid. Okay, so k-means clustering is a very easy technique to do. It's not very difficult to understand. So if you can use something this simple to do a load profiling, that would be really good. Okay, because we know the underlying concept very clearly, and if I can do something, demonstrate something with that simple technique, then it should be good. Okay, so let me go to the program that we have to see. 1 minute. Okay, so now let's go back to our program that we are supposed to see, and let me start with how that community is created. Now, how did I create that community load profile? So you can find that there is an industrial load that I have given, that I have generated. So all the load data is generated synthetically. If I had smart meters and if I had access to actual load data, then that would have been very good. But unfortunately, I didn't have any means to get the actual data. So I have synthetically created the data for each kind of load. So industrial loads, I have created a representative data. That doesn't mean that I have used only this profile for all the industrial loads. Okay, coming into the next stages, I will show how I have varied this data and actually tried to make this synthetic data representative of the actual data. Okay, so these four lines, these 5 lines create 5 different kinds of load data. Okay, so industrial load, residential load 1, residential load 2. You remember we saw there are working professionals and there are retired people. So residential load 1 and 2, 2 different type of houses, and then the commercial load, and then some random load which is not coming into any of these 4 categories. So those are the 5 different kind of loads that I have created. Okay, now if you take it to an actual practice, actual situation, and if you have load data from the actual meters, then you can substitute that thing here and then proceed from that. Okay, so this is again, I'm repeating, a representative load data for different categories of loads. Okay, so what is that I would like to see after I do all this clustering? Okay, now if I take in the industrial load, IND load is standing for industrial load, it is having some load distribution. Okay, so if I plot this, I will have a load curve. Okay, so if I take if I come here and plot my industrial load, let me plot it. Okay, it has not been initialized. I'm sorry. Okay, that's why it's saying. Okay, now let me copy this, paste it here, and then plot it. So this is the representative industrial load. Okay, so like this, I can plot every kind of load, the basic load that I have taken. Okay, so if I plot these loads, there will be 5 representative loads that I am taking. Okay, now after clustering, what is it that I would be looking for? I would be looking to recover these indicative loads after clustering. That would be my objective. Okay, so if I can, after doing all the variations that I do on these load types, after I mix them up, randomly shift them, mix them up, and create a data set, and I then cluster them, what is it that I am trying to find? My objective is to come back and extract this load profile from the data set. Okay, so that is what I'm trying to do. Okay, so we have started with what we want to achieve in the end. Okay, so that is where I start, and then I go further. So when I run it, you will find there are a lot of plots coming up, but I would like to show you how the synthetic data is generated. Okay, so the housing, the 2 types of houses, I have taken 200 houses belonging to the type 1 and 500 houses belonging to the type 2. Okay, and then here I do something called the circular shift. Okay, because if I have 2 houses of working professionals, okay, each working professional house, I would expect one peak in the morning when all the people are getting ready to go to their jobs and all the children are going to the school. So I will find a big peak in the morning, and then very low load during the daytime. And when all the people come back to the house at varying times, the children come back at 4 and the professionals come back around 6 or 8, and then you will find a peak at the night, the evening and night. Okay, so that is a kind of data that you would find if I am talking about houses belonging to professionals. Okay, but if I can't be taking that kind of a assumption without making changes into it. Okay, some houses will, some houses of the professionals will require more load. They will have bigger houses, 5 bedroom, 4 bedroom houses. Some will have 2 bedroom houses. So the actual load will be smaller or larger, and the time at which these peaks occur also will be shifted a few hours this side or that side. Okay, so circular shift is a command by which I can shift the load. Okay, so if I have if I create a vector 1, 2, 3, 4, 5. Okay, I just create a vector, and then if I say circular shift, shift, A is my variable, and then I say 2. Okay, then you can see what happens. Then what is happening is the values which these 4 and 5 get shifted to the front. Okay, so 1, 2, 3, 4, 5 is the value of A, and circular shift A comma 2 shifts the last 2 values circularly to the front. Okay, if I write it as -2 here, it will shift the other direction. Okay, so 1, 2, 3, 4, 5 is the original value of A. Circular shift A minus 2 will shift 1 and 2 to the back. Okay. Previously 4 and 5 from the back were coming to the front. Now 1 and 2 have been shifted to the back. So this is what a circular shift does. So I have used that to vary the peak timing of this these loads, and then I have also scaled it up with a random value. So some of the values of these loads will increase 5 times or randomly between 1 and 5 times. Okay. So they are not integers. It will go from all the way continuously from 1 to 5. Okay. So that is what I have done in creating different types of H1 load. Okay. So like this, I have created a H2 load. I have again shifted it randomly, scaled it up. Okay. Similar things I have done with industrial load, and there you will find the industries. I have scaled it up 50 times. Okay, 50 plus 50, so it will go up to 100. So the base value is 50, and then it goes up to a value of 100. And the shifting also, you will see that is also random. The shifting is also random, and it is random by how many hours. What is the maximum hour that I am shifting? That is shown here. So every type of load I am shifting with different hours, creating a random mix. I am scaling them up randomly. So I am not maintaining the same starting value of load curves. Okay. So H1 house, H2 house, commercial load, industrial load, and random load. All these loads I have shifted and mixed and circularly shifted and randomly scaled up. Okay. So I think that in a way should be very near to what you will see in a small community. That is the basis on which this entire exercise is done. Okay. So are you convinced with that kind of an assumption? Anybody having any comments on that starting point, or you see that is some sort of a manipulation? Yeah.
Participants can raise the hand if required.
Yeah. Please, I would be happy to hear some voices. Okay, some feedback voices. Then I will know you are really there. Otherwise, I'm not very sure in the afternoon hours whether you are really there, mentally and physically. Yeah. So some of you can. Anyone? Any comments? Okay, Srikanth has replied. It's okay. It's clear. Thank you, Srikanth. So I think, and Shajish also has replied. It's clear. So I think we can go ahead. I think it must be quite clear to others. It is not about clarity. What I was looking to see is whether you feel this actually represents a kind of data that I will get in a practical situation. Okay. So that is what I was trying to see. See, I have taken 4 different kind of loads. I have shifted them randomly. I have scaled them randomly. And I am trying to mix all that and say that is a community load profile that you will get. And from this, I am trying to extract these load profiles back with clustering. Okay. Now, it is a very, very nice example of machine learning, very simple machine learning technique, and it's very effective. But all that is lost if you're not convinced about the authenticity or the suitability of the data. Okay. After all, if the data is not correct, it is manipulated, then the results cannot be trusted. Okay. So that is what I was trying to see. Usually at this stage, some people will object. No, this is not truly representative of the data that I will find in a practical situation. So anybody having such feeling? No. Okay. So I will continue. So we go back and so now what I have done after that is after creating all this data, you will find that see this up to this, all the commercial load, industrial load, all that have been created. Okay. Then after doing all that, I'm going to put a sum of all these loads. Okay. I'm going to add all these loads. So sum of residential load 1, residential load 2, industrial load, commercial load, and random load. I am going to sum up all that and show you what is a, so figure 7 will show you what is the total load seen by the utility. Okay. Now, utility has access to the total load. It also has access to all the meter loads. Okay, all the metering data. Okay, so not that it is not that the utilities right now, if I talk about a utility now, it can only see the total load because it cannot see all the meter loads at every hour. Okay, so that is a big big change between a smart grid and a conventional grid. Okay, so this kind of an analysis would be definitely not possible in the present scenario where the utilities have no access to consumer load profile. Okay, but this particular scenario, what we are discussing, is in a smart grid, and the utility has access to the total load. It also has access to all the individual loads. Okay, so please keep that in mind. And that is the figure that I have shown in the PowerPoint. The whole set of loads shown as a random surface. You saw that how random and difficult it looks to visually find any pattern in that load. Okay, so now I've added all these loads, created a total load. Then what I do is, then we come to the section here where I am creating, I am mixing up all these loads by normalizing them. Okay, K-means clustering would work well if you normalize it. If you don't normalize it, in fact, in this exercise, if you don't normalize it, if you don't do this line, okay, where I have taken a particular load and then I divide by the maximum of that particular load. Okay, so I normalize it, bring the values between 0 and 1. So if I don't do it, okay, then what happens is loads do not get clustered properly. We'll discuss how this is going to be done and in how many dimensions are these clusters going to be formed. We have seen some 2-dimensional clusters. We will see what is the dimension required to cluster this. Now, if I don't normalize this, you can remove this normalization from the code that I will provide, and then you can run it and then see the results and try to analyze the results. Okay, so for proper working, I need to normalize it, and that is what I have done in this line. Okay, then what I am doing is I am shuffling, I am randomly shuffling this data. I don't want all the house data coming consecutively. I don't want all the industrial data appearing consecutively. So I have done a random permutation. Perm is a random permutation command. So I have done random permutation on this data and mixed up all kind of loads. Okay, so I have commented here, randomly shuffle the load matrix for a healthy mix of different load types. Okay, so that is what I do in this section. And this pair pool and these things what I have commented is if you want to run MATLAB in parallel mode, if you have multiple cores in your, I'm sure all of us have more than one core in all our laptops. So if you have a large number of cores in the laptop, you can run it in parallel and save some time. So you can uncomment these lines and then run it. Okay, then ops, this stat set, this is telling the k-means function that only the final results need to be displayed. Okay, so I am setting some optional options in this statement with that command, and here is what is the k-means function that I'm calling. Okay, so what I have done, if I go through all the previous steps, what I have done is I've started with 4 basic types of loads. Okay, then I have randomly circular shifted the loads and then randomly scaled them up so that it mimics a natural way in which it will appear in a practical community. Then I have added those loads and created a total utility load demand. Then I have mixed up all these loads. After normalizing the individual loads, I have mixed them up, randomly permutated and mixed up these loads, shuffled the loads so that there is a healthy mix of loads. Okay, no 2 housing data and no industrial loads should come consecutively. Okay, so that kind of a shuffling I have done. It actually makes no difference in the actual k-means procedure. But if I am showing you a load profile, if I had all the household loads together, you would be able to see a pattern. Now that I have shuffled them, you are not able to see the pattern. So that is, it is only for a visual authenticity. Okay, so that so that is what I have done. So that those are the stages that we have passed through, and here I call the k-means function. Okay, so it's just a k-means function called with the 5 number of clusters that I want is 5. So I ask it to do this clustering into 5 clusters, and then it returns the cluster index and the cluster center. Okay, so that is what it does. And then I go to that and then take the centroid of each cluster, and then I reconstruct my load profile. Okay, so that is what will be done. And these reconstructed load profiles that I get from the 5 centroids, because I'm putting them into 5 clusters, I'll get 5 centroid values, and those 5 centroid values will be able to give me 5 representative load profiles. Okay, then I will plot those representative load profiles. That is what I have done here. So, okay, so, from the centroids 1, 2, 3, 4, 5, I am plotting the load profiles, and then we will look at the result. So this is what is being done here. I don't know. I think I will run it, and then we will see the results, and maybe then go back, and if anyone has any doubts, then we will go back and see whether we can explain the results. Okay, so let me run it. So it has created a few figures. So let me start from the first figure and see what is happening. Okay, so these are the first figure shows where I started. Okay, this figure is what I started with. Okay, the blue one is the commercial load, the red one is the industrial load, the orange one is the residential load one.
Oh, we couldn't see the figure.
Yes?
We couldn't see the figure.
Oh, you can't see the figure. Okay. Oh, okay. 1 minute. Okay. I think I have to share that particular figure, is it not?
Okay.
Okay, let me see. Yeah, now can you see the figure?
Yes, coming.
Okay. Now the first figure that comes out is the point where I start. Okay, So these are the five different type of loads that I started with. This one is the blue one is the commercial load. This one is the industrial load. One is a housing load, one type of housing load, the other type of housing load, and this bottom one is a random load. Okay, so these are the loads with which I started. The first starting point of my program. Okay, this is what I start with. The next stage, what I'll do is, you will find that if I have hourly data, then it has quite sharp spikes, because they are linearly interpolated between one point and the other point. Okay, so in the next slide, next figure, I would have rounded off these to make them look like natural load data points. Okay, so that will be what will be the next figure. So I will close this figure. I will show you the next figure. Okay. So there are 11 or 12 figures. So this is the next figure, figure 2. Okay, now you can see it is the same load figures, but they are rounded. Okay, they look like more naturally occurring load profiles. Okay, nothing more. Okay, so that is what is done in the next figure. And the third figure. Okay, so this is the third figure. So now what I have done is, I have taken one kind of a load, H1, the housing type 1 house, where you have the retired people. Okay, the type 1 house is people with retired persons. So that house, I have created the entire randomly circularly shifted and scaled data profile. Okay, so this represents all the H1 houses that I have. I have 200 numbers of H1 houses. So if you remember what you have seen in the program, you will find that the H1 value is 200, and these are the 200 different H1 type of loads that I have created after circularly shifting and randomly scaling. Okay, so in this, if you can see that there is a particular visual uniformity or some sort of a relation that is there, and that is to be expected, because those type of houses will have a similar load profile. Now, it is not necessary that every day in the whole year this kind of a similarity is to be seen, but most of the time you will be able to find on most of the days some sort of this kind of a correlation between those kind of loads, those kind of similar loads. Okay, so that is what this conveys. Okay, so figure 5, 6, 7, all these are for different loads that I have taken. Okay, so I will not spend time on all that. Okay, let me go to the figure 7. And figure 7 here shows the sum of all the loads. Okay, so 200 H1 houses, 150 H2 houses, a few 50 numbers of commercial houses, commercial loads, some industrial loads, some random loads, all that put together. What is the load profile that the utility is seeing? Okay, if I have all the different kinds of loads added, then what is the total load demand that the utility is seeing? So this is the total load demand seen by the utility. So we see that around the morning hours you have a dip, and then nearly at 10 it goes up, and throughout the evening hours or night hours you have a very high load demand. This kind of a load profile is not corresponding to any individual load. Okay, it is a mixture of all these loads reflected in this total load demand. Is that clear? Okay. So that is what we have there. And now let me go to the interesting part of the. So okay, now let me go to figure 10. Figure 10 is what we started with. Okay, this is the figure of the different kinds of loads we started with. Okay, now why this random load has suddenly gone up is I have normalized all these loads. Okay, so if you have seen the original figure, you would have found this random load somewhere at the bottom. Okay, I will show those figures again, but then you will find this random load at the bottom. Now that I have normalized all the loads, okay, there is the shapes of the loads are maintained, but they are scaled differently. Okay, so and the objective of my exercise is only to find the shapes of individual types of loads. I'm not trying to find the magnitude of the representative loads. I am only interested in preserving the shape. Okay, I know that if I have a shape, then I can find what is the consumption of that particular load because I have all the smart meter readings with me. Then I will be able to scale up these loads and do some analysis on it. So preserving the shape is enough for my exercise. I don't have to preserve the magnitudes. And anyway, k-means clustering is not effective if I don't normalize it. Okay, so that is one of the limitations of this. Okay, so this is the normalized load profile that I start with. Figure 10 is that profile, and figure 11 is what we should be looking at, because that is a reconstructed profile. Okay. Okay, 1 minute. Okay. So figure 11, we have seen that when I called k-means, I called it with a parameter that asking it to put 5 clusters into the data set, and the 5 centroids are returned, and from the centroid values I can reconstruct what are the 5 characteristic load shapes. Okay, so this is what I get. After doing all that exercise, this is what I am getting. So this is my result. Okay, and you can see very similar to what we started with. There is a very similar random load curve on the top, and the remaining load curves don't exactly match. To compare them side by side, I don't think I can share 2 figures. Is it possible, Professor Shashi? Is it possible?
This MATLAB figure, right?
MATLAB figure, yes.
Okay.
Can I share 2 figures, or it is possible to only share 1 figure?
No, you can share. I think you have just
any number of figures. Okay, okay. I will try that. Maybe it will become smaller, but I will try that. Okay. So let me try to share more number of figures, maybe 10 and 11 together. So that it will make more sense. Okay, so I don't know how to select these 2. Okay, I'm not able to select.
No.
Anyway,
you're just using the window sharing, right? Or
I'm sharing windows. Yeah, window sharing.
yeah, the other mode you try. There is one more mode, no? In that, the entire screen will be, entire computer screen will be visible, no?
Oh, let me see. Okay, the tab sharing, is it not?
Yeah, just try.
Yeah, I'll try. Okay, the entire screen. Okay,
yeah. Your entire screen. That will try.
Okay. Let me try that. I was afraid it will not be very clear. Okay.
It's okay, I think.
Yeah. Okay. Let me try that. I don't know now what is it showing. Let me try the MATLAB. Figure 10. Maybe I can minimize it a little. Yeah, and figure 11 is somewhere. Figure 11 is not to be seen. 12. There is no figure 11.
Let me see one figure. I don't know what is the number of that. 11, I think.
You can see another figure?
One
Where?
figure I'm able to see.
Okay, one figure is 10. That is 10. And there is no 11. Okay, what I will do is, I think one figure is vanished. Okay, so let me, figure 7 is here. 1 minute. Let me minimize that. 3 minimize, 2 minimize, 1 minimize, and 10 is here. I can't
Now we can
find.
see multiple figures.
Huh?
Now we can see multiple figures.
Yeah, now you can see multiple figures, but the figure that I wanted to show, figure 11, is not to be seen. Okay, one minute. Let me run it again. Maybe it will come back. Okay, let me run this program again. It will take only a second to run, and all these figures will appear. Okay. So there is figure 11, and here is figure 10. So these two figures are what we require. Okay, so let me make it larger. We need only two figures. So side by side, let us compare and see whether there is any similarity in the point where I started and the point where I ended. Okay, so these are the figures. Figure 10 is where I started, and figure 11 is what I get reconstructed from the centroids. Okay, so this part, this random load seems to be preserved. Okay, that seems to be very close to what it was. Okay, and this blue figure, this blue curve with a curve here is appearing here. Okay, so that also seems to be preserved quite well, apart from the distortion at this point. Okay, at this initial stages. Okay, and then the yellow curve and this pink or magenta curve, all those have some distortions. Okay, you can find there are distortions in the beginning of this curves, and but more or less I could say that the shapes are preserved. If I take this this curve here, which is green here, what I'm showing, it has a hump in the morning, and then it has a bigger peak in the evening. So you find that has a relevance here. This is a curve with a peak in the morning and then another peak in the evening. So some of the figures are quite remarkably reconstructed, but there is some distortion in the beginning hours. Okay, so this is a result that you get. This is a honest result that you get from a simple k-means implementation. Okay, now we can discuss whether anything useful can come out of this kind of an exercise, and what can be done. Can I try more sophisticated clustering techniques to come out with better results, or what can be done to improve this? Okay, now are you clear about what is the whole exercise that we did, and what kind of steps we went through, and are you convinced about the results that you got? Have you seen the comparisons of the results? I think I need some comments here before I go and suggest improvements. Okay. So anybody would like to comment? I think Nambiar sir is there. Sir, I don't. Nambiar sir ഉണ്ട്. Nambiar sir, I don't know. Sir കേട്ടിട്ടുണ്ടായിരുന്നോ sir? ഓക്കെ, അപ്പൊ സാറ് വല്ലതും കമന്റ് ഉണ്ടോ സാർ? I think we can't hear, Ella. I don't think the mic. I am not able to hear. I don't know whether sir is speaking. Huh? Okay. Anybody else? Please. There are a lot of computer science youngsters here. So for them, this should be very simple. But it is a very practical journal article. I can give you references to journal articles. There are very good journal articles, exactly similar to what we have done here. And if you read that, you can see even a simple technique like this, if you can make out, if you can profile the load data, what are the kind of advantages you get, and it makes a lot of difference to the utility companies. Okay, so I talked about the motivation for doing this. You will find that a simple exercise like this helps them to achieve most of those points. Okay, so I can share some references which will highlight the utility of simple techniques like this, and definitely more sophisticated techniques will give better results. Okay, but I would have been happy if I had heard some feedback. I don't know whether I can call people. Thambati madam is there? Sindhu Thambati madam is there? I think I can ask her. Thambati madam is there, yes, so yes. I can ask her confidently, because I know her. Okay, so madam Mandangilum, any comments?
It's good only, but my doubt is like when you're clustering it, no, like how you're going to define the number of clusters.
Okay, yeah, that's a very good
basic say usually when you're doing any power system problem, that main confusion is like that only, how we are going to select the number of clusters.
Definitely. So that is a very valid point, and it's quite difficult to answer that actually. Okay, otherwise madam will not be asking that. Okay, if there was a simple answer, everyone would have known it. But I will come to that, ma'am. I'll come to that. Possibly the computer science people are not asking that question because they are not very familiar with electric load profiles and power system aspects. Okay, that might be the reason why they are not caught on that point. That is a weak point in this presentation. Okay, so let me come back to that. Okay, then here, see, I have done. I have given a. I think I have to stop sharing. Is it visible? Is my screen visible now? So I have highlighted the k-means command. I have highlighted, and I have given 5 as my cluster. Okay, I have asked the data to be clustered into 5 units.
It's not visible.
Not visible, huh?
Not visible.
Okay, I don't know why that is so. Okay. 1 minute. Huh? Yeah. Now is it visible?
Yeah, it is coming.
Okay. So now, if you look at the program, I have called k-means with a value 5 here. Okay. If I change this value, okay, if I make it 6 or 10, because as madam says, we don't know how many type of consumers are there. And I don't know to how many clusters should I cluster this data. Okay, but if I look at a smart grid, okay, if I look at a smart grid, I have a lot of information regarding the consumers. Okay, now from where I am talking all this is from the journal article that I read. So they say that in that article they say that in a smart grid, lot of information regarding the consumers is available with the utility. Okay, and usually the utility has a very good understanding about what type of consumers are there in that particular community. I'm talking about a small community. So usually the utility knows what kind of households are there, what kind of industrial load is there, what kind of commercial load is there. And if they look at the smart meter readings without much of an effort, they can see patterns that will point to a particular number of clusters. Okay. Now, if I look at the grid today, if you ask me the question, if I take the grid today without smart meters, and if you ask me how many types of clusters should I put them into, I would have definitely no idea. Okay. But when it comes to smart grids, when I have smart meters giving me every 15-minute data, then I have all this data with me. I don't have to do anything with the data. If I just observe the data, I can see patterns which will help me to get a starting point on how many clusters are required. Okay, so I can start with that value. I can cluster them into those numbers. Suppose I say the starting point is something like 7. Okay, suppose I put 7 here. Okay, and then if I run this, I think there is a power failure here. I hope the internet is still going on, is it not? So
yes.
if I have a number 7 here, and then if I start it, then I have to add some more points here. Okay, let me add those plots, otherwise you'll not be able to see. Let me copy and paste this and create 7 centroids here. Okay, so I have started with 5. I made that data set with 5. Now I want to look at 7. I don't know how many clusters are there, so I start with the value 7. Okay, and I run it. Okay, so this is the result that I get. Now I will show you the result. I will share the entire screen, and then you can see what is the what happens. Okay, so 1 minute. Please give me a minute. I will. Yeah. Okay, now can you?
Yeah, it's okay.
Can you see the two figures? You can't see it, is not?
No figure.
Yeah. I'll bring them up. I'll bring them up. Don't worry. Okay, figure 10 and figure 11. So this is what I started with, 5 load curves, and this is what happens if I do the centroid as 7. Okay. Now, if you look at it, the random load is still preserved. One of the load types is still preserved, because it will be a cluster that is very distinct from the others. Okay. So if I have a cluster which is far separated from the other clusters, then that will be preserved. Okay. The remaining load curves that I started with have been totally, I think all the other remaining load curves have been totally distorted. Okay. And there is one cluster, one curve here, which has a peak in the morning, the early hours of the morning, and it has a dip in the evening. Okay. So one is a totally disjoint, totally unrelated curve here. Okay, so if I accidentally start with a different value of clusters, if I look at the results, if I take these results and look at my smart meter readings, okay, I should be able to find out that this is not the optimal number of clusters. Now that is a very simple way of doing it. There are statistical methods of doing it. So you can statistically analyze the results of different clusters and see which type of clustering most matches with your smart meter readings, because this would not have been possible if the smart meter readings were not available. Okay, that then we would have been blind about the kind of customers that are available. Okay, but now I know the smart meter readings. I can always go back and see statistically which is the optimal number of clusters that can be used. I think I'm not qualified to go into too many details of that because I'm talking about a journal article. I think, Madam,
Yes.
I don't know whether I answered.
Yes, Venu, yeah. Yes,
Yeah.
Venu. And one more doubt. One more doubt I'm having is like suppose we are having so many dynamically varying load curves. We are having different pattern loads. We are having.
Yeah.
And it's all it's a dynamically varying conditions. When we are loading all the patterns, whether is there any algorithm which will say that you'll be getting an optimal number of centroids for that?
Dynamically varying load patterns, do you mean stationary in a day, or there is no stationary quality at all? It is varying. Suppose I take a household. Suppose I take a household load. You are saying that every day it will have a different pattern.
Yeah.
Okay. Okay. So that kind of a situation, I don't know whether practically we will see. I don't know.
Because this is what we experienced. This same condition. It's coming in the generation side also. Like when you are integrating renewables to the grid, no, this type of dynamics are coming to the system. So we are not able to predict it properly.
Okay. Oh yeah, I get that. Yeah, that is a totally different scenario. See, that is what we have lots of tools in machine learning. I have used the simplest, I think the rock bottom in complexity
it's there
to demonstrate.
That is there available there, no? It's already there. It's
this is there. This is already there. So I have used this to just to motivate people to look at machine learning for power system. Okay, so if you have variable generation, you have renewables integrated with high variability. The generation itself is highly variable. Then you, like you say, it is very difficult to handle with k-means. Okay. Then what we will have to do in that case, even if it is varying, if even on the surface, if this generation is variable, there will be some probability curves, probability distribution that I can
integrated with this.
Yeah, that can be associated, and based on that distribution, you can do a k-means clustering.
Okay.
So instead of taking,
separately we have to consider.
Yes. So you can't do it on the power generation directly. You will have to take it into a probability distribution of that variable generation, and then do a clustering on that, and then reconstruct whatever you want to reconstruct.
Okay. So separately we have to do from both sides. So
Yes.
Thank you, Vinu. Thank you.
Yeah, thank you. So at least
by one of the student, advantages of shifting the load curve.
Advantage of
shifting the load curve by
shifting the load curves. Yeah, I mean, I'm a professional. Shashi is also a working professional. He gets up at 4 o'clock. I get up at 7 o'clock. Simple answer. We are all working professionals, but we get up and do different things at different times. So our load peaks will appear, even though the shape may be the same. They will be shifted a little according to our behavior and our activities. Okay, so even though I am talking about all professional houses with the same number of bedrooms and other things, they can have time shifts. Okay, so I have to realistically create a database for doing this k-means clustering. It's just an exercise to do that. Okay, there's nothing else. Yeah, anything else? I don't know whether I answered it properly.
Yeah, Venugopal, it is Nambiar.
Sir, Paryu sir.
എൻ്റെ മൈക്രോഫോൺ വർക്ക് ചെയ്യുന്നില്ല. ഡെസ്ക്ടോപ്പിലെ മൈക്രോ വർക്ക് ചെയ്യുന്നില്ല. അതുകൊണ്ടാണ് ഇപ്പോൾ മൊബൈൽ ഫോൺ സംസാരിക്കുന്നത്.
Yes, sir.
I just want to ask the same question as asked by Dr. Tambati.
Yes,
So I am
yes,
not
sir.
repeating that question.
Yes, sir. Yes, sir.
I want to compliment you for your excellent presentation
Oh,
on a
thank you, sir.
topic
Thank you.
which is quite
Thank you, sir.
useful to the power
Yeah.
system engineers.
Yes,
That's
sir.
right.
Yes, sir.
Yeah, I just wanted to one more question.
Yes,
When
sir.
you make cluster of loads,
Ah.
does it have any dimension, 2-dimension or 3-dimension like that?
That is one question I was expecting, sir. Nobody asked. I don't know. I wanted to conveniently ignore it, but now that you asked, I will answer that. Okay. I was hoping some computer science people will jump at this and demand to know what is the dimension of the space in which it is being clustered. Okay. So I have taken hourly load data, sir. And
Yeah,
there are 24 values for each type of load.
Yeah,
Okay, so
hourly load.
each point in that data set is having
Yeah.
24 dimensions.
Yeah.
So this clustering is done on a 24-dimensional space, and each data set is one point in the 24-dimensional space.
Okay.
So that is how it is clustered. So usually when computer science people are asked whether time varying information can be clustered with k-means, they will immediately say no. They'll say there are some other time series techniques and other techniques for doing this. K-means will not work. But it is very simple to do it with k-means, because you can always consider a 24-hour value to be a 24-dimensional point, and then you can still cluster it.
Okay.
And that is possible because I am normalizing the load curves. If I don't normalize it, then the correlation will be lost.
Oh, that is why you go to normalization of the
yes, sir,
random,
yes, sir,
yes. That
yes.
random load. Yeah. Okay.
Yes, sir. Yes,
okay.
sir. Yes.
Yeah. Thank you. Thank you very much.
Thank you, sir. Thank you. Thank you, sir.
Oh,
Thank you for bringing out that point, sir.
Yeah.
Shashi, I don't know whether.
Any more? We will ask participants. Any more questions?
Yeah.
Participant side.
No. So I think I will provide these programs and Excel sheets and everything, and I will also try to give you some references which will help you to read further. Okay, because I have just covered the surface, just touched the surface. There is a lot of depth required to do some practical work. So I will send the references and the simple programs that I have written. Thank you for patiently giving me a hearing. Thank you, sir.
Thank you. Thank you. Nice presentation, Venu.
Thank you. Thank you. Thank you. Nice to hear from all of you. Thank you.
Thank you. Thank you.
Thank you.
Shashidharan, can you share that videos and recorded videos and all this?
Madam, we will provide. We will provide.
Okay. Okay. Thank you. Thank you, Shashi.
And tomorrow we are having sessions until Saturday. So anyone interested from Amrita University can also join. I will provide the links, everything.
Okay. 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 We are having the schedule, total schedule we are having.
Yeah. You're having, no?
Yeah, schedule is there, but meeting link is different, no? It's not
Yeah,
a common.
I will send. Okay.
Okay. Okay.
No, ma'am, it's the same meeting link. It's the same meeting link.
Oh, same meeting link. Okay. Okay.
Yes, ma'am.
So with the same link we can join tomorrow's session.
Every day.
Sure, ma'am. Sure, ma'am.
Okay.
Until 19th, we have sessions. You can join.
Okay. Okay. Thank you.
Madam Sindhu ma'am, you
Yeah.
can also send us some links, because I am sure there are a lot of interesting FDPs going on in Amrita also.
Nowadays we are not doing anything.
Okay. Yeah, COVID.
And also I think all this online classes, everything. I don't know.
Oh, everyone is busy with other
yeah.
activities. Okay. Yeah.
If it's there,
I
we'll
think
say.
Yeah, sure.
And
Thank
also,
you.
we also will invite you for our FDPs also.
Oh, thank you. I would love to do that.
Okay.
Yeah. Okay. Thank you, ma'am. Thank you.
Team, please.
Thank you, sir, for your inspiring and informative session. We convey our sincere gratitude to you, sir, for taking time out of your busy schedule and to come here and spend it with each and everyone present here. Thank you, sir.
Thank you, Shashi.
There is one more announcement. The feedback link is provided in the chat box. There is a general reminder. According to AICTE rules, a test must be conducted on the final day of the session. The test will be objective questions and score of 60% and more is mandatory. Attendance of the participants will be taken via Google Meet, and the participants with more than 80% attendance will receive the certificates. Thank you, everyone. We'll meet again tomorrow when we have the session on artificial intelligence and neural networks by Dr. Sheji Mohan from GEC Kozhikode between the hours 10 to 11:30 and 12 to 1:30 IST. Then we have Dr. Shashidharan Sridharan from MS College of Engineering between the hours 3 to 4:30 p.m. IST to talk
Excuse
about the
me.
topic.
One correction is there.
Yeah, link is not there. Feedback link is not there.
Feedback link.
Yes, sir, I have provided in the chat box.
No, it is not in chat box.
It's not in chat box. Please
Sure,
provide.
sir. Yes, sir. It's
Now it is
actually in the
in chat box. And you didn't send the feedback link in the second session.
Okay.
So actually, this both sessions are connected, sir. It's the same resource person doing about the same topic. That's why, sir.
So the feedback is attendance.
Sorry, sir.
Feedback means attendance is there.
Yeah, sir. Definitely, we need a feedback, sir. Your
Yeah,
feedbacks
yeah.
are fine
Matlab
for us to
feedback means
improve.
we are attended. We have attended this session.
Yes, sir.
And
Also, we also check. Also,
one
we are
last
checking the
question.
participants list.
How many questions are in the quiz? Last test.
It's just a general feedback, sir. About the questions, it will be we haven't sorted out yet. It will be like up to 10 to 15 questions, sir.
One second, one second. Others, please mute. Others, please mute.
15 to 20 questions are there. Sir, how much time is there?
So it will be like a small quiz.
Yeah.
Just general topics covering
Yeah.
the simple basic questions. That's all, sir.
Okay, it is in Saturday, last day in last session. Yeah.
Yes, sir.
Okay,
Last day.
thank you. Continue, sir. Continue. Thank
Sure,
you very
sir.
much.
One correction is there. Tomorrow afternoon, we will be having a session by Sarkudina, Senior IT Consultant, Saudi Aramco. Artificial Intelligence Big Data Case Study. Okay. She's the Senior Consultant in Saudi Aramco. Tomorrow afternoon, we session. My session will be on Saturday.
हेलो
Okay.
हाँ सर बहुत अच्छी तरीके सक्सेसफुली कंडक्ट
Okay. So we will wind up. Anything more, Sanat?
Nothing much, sir. If you have any doubts and queries, you can mail to us. We'll definitely respond to your queries. Thank you so much, sir. Thank you everyone for coming. Thank you, sir.
Okay, fine.
All the feedback links will be mailed to you. Please check your mails also. There is a feedback link in your chat box.
Sanjeev,